Yeah, welcome to my presentation on hybrid networks. It's actually from my master level course, Advanced Distributed Algorithms, that I give at Paderborn University. So I hope that the level is okay, that everybody can follow it. But if you do have any questions, please, feel free to raise your hand so that I can address that. Yeah, definitely. Oh, and please let me know if I'm getting over time or close to the limit of my time. Yeah, somebody just tells me like 5 minutes left or something like that. I don't know whether Phil or someone can do it, and so that I know somehow when I need to stop.
Yeah, I
Okay, that would be great. So let's get started. First, I will present some motivation and model, since that might be the first time that you hear about hybrid networks. Then I will talk about well-formed trees, minimum spanning trees, shortest paths, rapid reconfigurations, and if time permits, I might also talk about some open in this area. Yeah, motivation. We all communicate in a hybrid fashion. Yeah? We humans have multiple senses and we use them very effectively in order to communicate with each other. Though if you look at research on networking, most of the time we are just dealing with one communication mode. Yeah? But we are not really looking at combinations of communication modes. And that's what hybrid networks are all about. Yeah? Even though in practice people have already addressed that. For example, if you think about modern data centers, the servers, they are not just connected via some cable network, but they might also make use of wireless or optical communication, yeah, in order to establish dedicated connections between servers, which can be very helpful if you want to migrate, for example, tasks or data, so that it doesn't put a burden on the cable network, so that you can use it for like normal operations. Yeah, or for vehicular networks, a hybrid approach might be the one that you want to go for, where you combine communication via a cellular infrastructure with ad hoc connections to get the best out of both worlds. That's the basic idea about hybrid networks. So the question is, of course, how to model that. Oh yeah, and some other examples, of course, like social networks where you might have a combination of trusted links, trusted in a sense that you really know the people that you're connected with because they are relatives or like real friends and not just some online friends, yeah, that you met at some point that sent you invitations. Or multi-point VPNs. So if a company connects its headquarters to its branches, what they usually do is, if they're big enough and communication is important enough, they really have leased lines over the internet. So they have contracts with internet service providers that give them guaranteed connectivity, yeah, between the headquarters and the branches. But on top of that, the company might just use TCP/IP connections to communicate flexibly between the branches without always having to go via the headquarters. So also there, in some sense, you have two different communication modes with different behavior. So how to model it? Here's the approach that we have been following. A hybrid network H equals VLE is a directed graph consisting of a node set V, a set L of so-called local connections, and a set E of global connections. The local connections are not under the control of the algorithm, so they are either fixed or determined by some external events. I will soon give you some examples, while the global connections are fully under the control of the algorithm. So what do I mean by that? Yeah, let's look at examples. For example, data centers. What are the local edges? The local edges are the cables, yeah, the cables via which the servers are connected. Surely you can't just, go to this server area and reconnect all the time, right? The cables are fixed. Yeah, they are not in some sense under the control of the algorithm. While if you use optical communication between servers, right, you can redirect the optical devices so that you can flexibly communicate with whichever server you want to communicate with. Yeah, and in fact, these data centers, they have then like mirrors mounted under the ceiling so that you can really pinpoint to the right server whichever you want to reach. Yeah, so they are fully under the control. So there are two different communication modes. Car-to-car networks. The local edges are the ad hoc edges. Yeah? They are not under the control of the algorithm because they're depending on the speed of the driver, for example. Yeah? The algorithm can't say to the driver, yeah, please speed up so that I can keep this ad hoc connection, right? That doesn't make any sense. So of course, this is like under the control of some external events. Yeah, that's not under the control of the algorithm, but the global edges. So whenever you communicate via the cellular infrastructure, then there's no limitation, right? As long as, of course, which I assume the cellular infrastructure is around. Also there you see these different communication modes. Or multi-point VPNs. The local edges are the least lines. Yeah? They have been established via contracts. Yeah? And so the algorithm, they cannot just flexibly change the contract all the time. Right? They are fixed. They are normally long-time contracts. You just use them as they are given. While the TCP connections, they are flexible. Yeah? You can connect via TCP/IP to anyone you like via the internet, of course, but then you just get best effort service. While for these lines, you get guaranteed service. Yeah, so that's the basic approach concerning hybrid networks. Yes, first question.
So just to ask, now you say the connections are fully under the control of the algorithm, the global ones.
Yeah.
Does that mean the algorithm can change this graph?
Yes.
Okay.
It can change
It's
the
not
graph.
a static graph, so it's
Yes. And I will also give some more details about this one, what I mean by that exactly. For simplicity, throughout this presentation, I will just use the synchronous message passing model, yeah, in order to use these different communication modes. That's like the most simple thing. Of course, you can do lots of things also under the asynchronous message passing model, but this is just, complicating things, and I don't want to, be too complicated here. I just want to have a message passing model that is as simple as possible, which means that the nodes, they are operating in synchronous rounds, yeah, and in each round, a message sent from a node U to a node V via a local or a global edge in round I will be received by V at the beginning of round I plus 1. Yeah, the most simple message passing model you can imagine. That's what we'll use so that we, get the main messages across here. Of course, what I haven't said yet is how many messages can a node send or receive per round. And that really depends on the communication mode, whether it's local or global connections. So here really I distinguish between these different modes. For the local connections, I assume that the connections between the nodes are real, like there's real cables. So the amount of information that a node can send and receive depends on the edge capacities. Yeah? So if a node has like many edges to other nodes, then it can send and receive a lot of information. Yeah? It's like the sum of the edge capacities. Otherwise, if it only has a few connections with possibly low edge connectivity, edge capacities, then it can only send a few bits per round. And I usually assume that all edges, all local edges are bidirected. Yeah? So I just draw them as undirected edges. So communication can always happen in both directions for the local network. For the global connections, we assume that this communication is over some shared infrastructure. And the limitation here is the connection that the node has to that shared infrastructure, like your connection to the internet. Yeah? I assume for simplicity that this is the bottleneck. So we don't have edge capacities, we have node capacities. Yeah? So the number of edges that you have to other nodes is completely irrelevant. Yeah? Your connection to that shared infrastructure is what's the bottleneck. So there is a fundamental difference. However, the nice thing here is that you're completely flexible, right? So imagine that the shared infrastructure is the internet. Of course, you can be connected to, different computers at the same time via the internet, and you can also establish new connections. Yeah? Imagine that computer 1 knows computer 2 and 3. Then, for example, it can send the address of 3 over to 2, and then 2 can also establish a connection to 3, right? So I assume that for the global connections, you're completely flexible. You can change the communication network over time, as you like. However, in some sense, you have to have knowledge, right, in order to change the graph. So you can't just like come out of thin air with a new connection. No, it has to be given to you by some other member. Yeah? So we assume that there is some starting network that you start with, and then via local introductions, for example, you can then change the connections over time. That's the basic idea. Any questions up to this point? So the local connections, these connections are kind of given, fixed. They might change over time, but then it's due to external events, yeah, that are not under our control. While for the global connections, we have like full control over the connectivity, and we can change it as we like. Yeah, so that's the main difference between the two. And while for the local edges, I have edge capacities, for the global edges, I have node capacities that are the limiting part. Okay, so now we clarified a lot of details. Yeah, so we have this hybrid network with these two kinds of edges. We have the synchronous message passing model. And just for completeness, for the local edges, this is also a well-known model. I use the congest model, which means that in each round, I can send log-n bits via each edge. Yeah, so I can transfer a message of size O of log-n bits, which is enough, for example, to transfer addresses, node IDs, something like that. For the global edges, I assume that nodes can send and receive a polylogarithmic number of bits per round, yeah? Irrespective of the number of connections. Yeah? So a node, if it has a lot of connections to other node, it has to make a decision which nodes to go for in order to send information. And of course, if it receives more than a polylog n bit information, then we assume that some adversary decides which is dropped. Yeah? So that we really try to make sure that we are not overloading here the connections. Questions?
So do you abstract away other properties of the network, such as link jitters or delays?
Yeah.
Or
Synchronous message passing model as simple as possible. You can put lots of these things on top of this model, and that makes it, of course, more interesting and more realistic. But for that introduction here, I try to be as simple as possible. Yeah? Definitely, there is a way to go if you really want to have it as realistic as possible. Also, for the local and global connections, there might be different delays involved, yeah, for sending information along edges. So this is all things that you have to take into account. But I abstract from all of these. I assume that the amount of time you need for the local and global connections is the same. Yeah, and I use the synchronous message passing model for everything. Yeah.
Because you were saying that the local can be slow or so, but now you're assuming they're the same.
Yeah. So from that perspective, from the timing perspective, there's the same, there's no jitter, right? It's like everything sent at round I will be received at round I, at the beginning of round I plus 1. The most simple communication model you can imagine.
Also with respect to the nodes themselves, they are all the same for you?
Yes. Of course, also there for the nodes, you can distinguish between different like storage capacities and whatever, but we ignore that. Infinite storage. Although the protocols that I will present, they only need a very small amount of storage. So we don't need to worry about this. And also the computational complexity of these protocols will be very low. So we don't need heavy requirements for the computational requirements for the nodes. Yeah, you could use embedded nodes or something like that. Very simple to run these protocols that I will present.
So this is not meant for high throughput networks?
No, I'm not really addressing the high performance issue.
You're mentioning laser and data center.
Yes. In fact, there are some nice add-ons that you can do on top of it in order to study exactly these problems. If you want to have a look at papers on that, I can recommend papers by Stefan Schmid, because he looked at exactly those things, making use of these different communication modes in data centers. Yeah, so he has really looked at this high-performance computing things. He has distinguished between so-called elephant flows and mice, these things. So I can definitely recommend to have a look at his papers. Okay, why hybrid networks? Let me just give you some very simple introductory example illustrating the power of hybrid networks, that it's like more powerful, the combination is more powerful than the different communication modes by themselves. Yeah? So let's look at a very simple scenario where we have k clusters of k nodes each that are connected in this specific way. Yeah? And now let's assume that we just want to broadcast a single message from one node to all other nodes. Yeah? And this leftmost center node, yeah, this is the node that originally has the message. Yeah, that's what I assume. Now, if I just use the local edges, I definitely need at least k rounds. Why? I guess that's easy to answer, right? Because the diameter of the network is k, right? I mean, it's more than k, yeah? Because I have k clusters that are just connected to this list. And so the diameter is more than k. If I can just use the local networks, it takes omega of k many communication rounds for a message to reach all nodes, obviously. This is a bit more tricky. If I can only use the global edges, and I assume that a node can only receive a constant number of messages per round via its global edges, then I claim the lower bound is log k. Why? Can anyone answer this to me?
So the global edges are between the clusters.
The global edges can now be arbitrary. You can even choose them arbitrarily. So now I don't worry about how they emerged. You can pick arbitrary global edges. And I tell you the best you can do is log k rounds. Why? Because the node originally holding the message can only forward it to a constant number of rounds, let's say C. And these C nodes in the next round can also just forward it to a constant number of rounds, so it's like C squared. So in the next round, you have C to the power of 3. And so you need somehow the C to the power of log k to the base of C many rounds so that it makes it to k many nodes. Yeah, for sure. So definitely the lower bound is log k. There's nothing you can do about it, right? Even if you have this full freedom of choosing global edges, it's the limitation on the node capacities that gives you this lower bound. However, if you use both of them, you can do it in constant rounds. How? It's relatively simple. You first use the local edges to send it from the cluster center to all cluster nodes. Then you use the global edges so that each node of the cluster informs the center of a different cluster. Yeah, you need just one more round. And then all of the cluster centers then inform their nodes in their cluster. 3 rounds. Great. So you see the hybrid network is more powerful than the different modes by themselves. So it's kind of interesting, right? You can do more. And it's much more than just a logarithmic advantage, right? So there are several papers on that have shown that it's actually sometimes even a polynomial advantage that you have if you switch to hybrid networks. So it's like it makes a big difference. Okay, so that's the motivation I wanted to give. Yeah, just to show you, seems to be interesting. So let's look at what I consider the most simple problem for hybrid networks, namely the problem of forming so-called well-formed trees. Okay, what's a well-formed tree? An undirected tree T is called a rooted tree if it has a root node R, and every node V knows which of its neighbors is the parent and which are the children with respect to R. Yeah? So every node here knows, okay, like upwards is R and downwards are the children, right? And for all the nodes in the tree, they know that. Then it's called a rooted tree. An undirected tree of size n is called balanced if its diameter is O of log n. Well, you know that from basic data structures, right? You want to have a balanced search tree. And finally, an undirected tree is well-formed if it is rooted and balanced and it has a constant degree. Yeah? You can probably imagine why this is interesting, because what I want to do is I want to form a well-formed tree with the global edges. Because once I have such a well-formed tree, I can very easily spread information via my global connections. Okay, but more details on that later. So what I want to solve is now the well-formed tree problem. So given a hybrid network VH equals VLE with nodes of distinct IDs, so I assume that they're like pairwise different, yeah, where VL forms an arbitrary undirected connected graph, and the set of global edges is initially empty. Yeah? Set up global edges so that V, E forms a well-formed tree T on top of this original local network. Yeah? That's what I want to do. And of course, we can use the local connections as a starting point for the global connections. Yeah? That's how I start. Because you can imagine that the nodes can ask each other about like what is the ID, what is your ID with respect to the global network, yeah, with respect to the shared infrastructure, so that they can establish global edges on top of these local edges, and then they go from there. And the question is, how quickly can you rearrange these global edges so that you arrive at a well-formed tree? Relatively simple question. Okay, let's look at the most simple case, that the local network forms a line. And that's one node already knows it's going to be the root of the well-formed tree. Yeah? So lead election has already been done. Yeah? So most simple setting. How can I do it very quickly? Anyone already has an idea? Okay, so here's the strategy. So first of all, as I said, you can use the local edges to establish global edges between exactly the nodes that are originally connected via the local edges. Yeah? They can inform each other via the local edges here. That's my address via this shared infrastructure, so use that, and you can also communicate with me via the shared infrastructure. Okay, so then the global edges form a line. Of course, that's still far away from a well-formed tree because its diameter is too large. So what I do now is I use a well-known trick which is called pointer doubling. So each node introduces its neighbors to themselves, right? So 2 introduces 1 and 3 to each other. 2 can do it because now we are in this global environment, right, where they can exchange addresses of neighbors, so that now in the next round 1 can connect to 3, 2 can connect to 4, 3 can connect to 5, and so on, right? So via neighbor introduction, I can basically establish these so-called level 1 shortcuts on top of the line. And of course, now I can go on, right? So in the next round, now that 2 has level 1 shortcuts to 0 and 4, now 2 can introduce 0 and 4 to each other. And 3 can introduce 1 and 5 to each other, right? And 4 can introduce 2 and 6 to each other, establishing so-called level 2 shortcuts. Yeah, so now you can go on. And of course, it's easy to see because you see that if you continue with these neighbor introductions, you establish edges that are bridging a distance of 2 to the power of I after I rounds. Yeah, so the distance that these edges are bridging, this is exponentially increasing. At the beginning, it's just 1, then 2, 4, 8, 16, and so on. So in a logarithmic number of rounds, you're done. Yeah, there are no more shortcut edges that you can create. And the nodes will also notice that, right? They don't have to know n for that. They will simply notice that by not being able to continue, yeah? Because there are no more level I shortcuts that they get, so then it terminates. And now this is not the way how you might also have like 2 shortcuts, but okay. And then for each node V reached via a level I shortcut that has not already been reached before, traverse 2 level I minus 1 shortcuts in parallel, and tell the nodes reached by these that they are now the children. Obviously, the edges used by the search strategy form a binary tree of depth O of log n, so the overall runtime is O of log n. And we are done. We formed a well-formed tree. So for the line network, it's particularly easy to do that. Okay. Now, next higher difficulty. Now assume that the nodes initially form a tree. And even, let's assume that they even form a constant degree tree, right? And there is still, also there, a node knows that it's going to be the root. Yeah, just the most simple case, we even have a rooted tree. So the nodes even know in which direction to find the root, right? So the node knows which of their neighbors is the parent and which are the children with respect to the root. So it's really simple. So the only thing that's missing here is the diameter, right? Because we might have a rooted constant tree of large diameter. So I want to get the diameter low to O of log n. How can I do that? Of course, again, I establish global edges via the local edges, and in fact, I arrange them so that they form an Euler tour. That starts and ends at the root node. And this, of course, can be done via internal decision, right? They just come up with some internal ordering of the children that will basically determine how the Euler tour is going through the tree. Yeah?
Another question, do they know the topology of this graph?
Yeah. So they know that it's a tree, and every node, it's a rooted tree even. Like every node even knows what's the parent and what are the children with respect to the root.
They don't really know who the root is in this?
No, they don't know the root yet. They don't know the idea of the root. but they know the direction towards the root, yes.
Okay.
And they know it's a tree.
So for the previous example, they know they're on a line, but not where.
Yeah.
Okay.
Yeah. So red, they didn't know the direction towards the root, but it doesn't matter, right? For the pointer doubling, everybody would do the same, and they don't have to know where's left and where's right. Yes, exactly. So here, but I will also show you how to get rid of each of these assumptions, like that you don't need to know that it's a rooted tree. You just pick arbitrary trees. Things get more complicated. Okay, so they can easily arrange their edges into some Euler tour, right? And in some sense, they can, remember, it's like a constant degree tree that we are starting with. They can now, like each node can introduce a constant number of so-called virtual nodes, yeah, for the traversal, for the Euler tour traversal, and they number them according to the time when it's visited by this Euler tour, yeah? They know that because they internally decide in which order the children, in which order to visit the children, and every node knows what the parent node is, so where the Euler tour comes from. So they come up with this ordering, yeah, of virtual nodes. And now what you'd simply do is you just connect these virtual nodes of number 1, of label 1, so that are visited first along this Euler tour. And you can easily do it by doing this shortcutting, right? Because you can use, again, this pointer doubling approach so that you can directly connect the virtual nodes with labels 1. Basically now giving you this construction. Yeah, so that you like remove all these intermediate nodes that have labels larger than 1. And now you're back to a list. Yeah, to a directed list with starting point the root. And we are actually at exactly the situation that we were when we looked at the list case. Yeah, so we transformed basically the tree into a list so that we can now use the same approach that we saw for the list. Yeah, so that from that point on, I can now again establish shortcuts. I can come up with this binary tree, and this binary tree will just have a logarithmic depth, will have a constant degree, so that indeed overall, I do arrive at a well-formed tree, and the runtime is logarithmic. Any questions up to this point? Okay. So in summary, I reduced the tree case to the line case just via this Euler tour approach, yeah? And by doing this shortcutting along the Euler tour. Okay. Now let's talk about the general algorithm, the well-formed tree algorithm, yeah? Initially, every node V forms its own well-formed tree. So in some sense, we are using an approach that is similar to Kruskal's algorithm or Berufskar's algorithm, right? Kruskal's algorithm should be well known to all of you, right? It's used for minimum spanning trees, and it's done in a way that you like grow trees, yeah? Like you start with each node representing its own tree, and then you kind of merge them together. And that's also what we'll do here. So at the beginning, every node represents its own well-formed tree, and the root of this well-formed tree is equal to V, and the ID of the tree is also just equal to the ID of V. All nodes execute now the grouping stage and the merging stage in parallel for a logarithmic number of rounds, logarithmic times, and at any time, the ID of the tree, so there's an ID associated with each tree, is the ID of the root of the tree for any tree T. So now, how does the grouping stage work? First at the high level, I will give some examples later. Each well-formed tree T determines the neighboring tree T prime of highest ID with respect to the local edges. Yeah, so this is really similar to, in some sense, Berufskar's algorithm or Kruskal's algorithm, if you wish. So you investigate which tree are you like neighboring with respect to the local graph, yeah? And whichever has the highest ID, that is what you are trying to connect with via a global grouping edge. You try to establish an edge to that. Unless your ID is larger than the ID of the tree T prime you want to connect with, and T prime also wants to connect to you, because then it's a redundant connection, and then you drop your own grouping edge. I will soon give an example on that. The merging stage now works as follows. So every global tree resulting from the grouping stage merges into a single well-formed tree with new root being the root of highest ID. Yeah, that's the whole thing that the merging stage now tries to do. So that we are back to every tree representing a well-formed tree. Okay, here's a simple example. So remember at the beginning, every node represents its own well-formed tree. And now they're just looking via the local edges at other nodes, trying to figure out, okay, which of the neighbors has the highest ID? So obviously, 5, for example, discovers that 6 is the node of highest ID. 6 also discovers that 5 is the node among its neighbors of highest ID. But since already 5 wants to establish a grouping edge to 6, 6 doesn't establish another grouping edge to 5. Right? Doesn't make sense because the connection would be redundant. Yeah, and for all the other nodes, for example, 1 would connect to 9, 9 would connect to 7, 7 would connect to 10, and so on and so on. Right? They always connect to the highest ID that they find in their neighborhood. And so basically you see that these grouping edges, they will result in these rooted trees. Yeah? Okay, here's another example, right? So here, I just switched the labels of the nodes like slightly. So here for like 3 I replaced like by 7, so 7 to 3 and so on. So I just switched the labels slightly, and then the grouping will look like this one here. Yeah, and what I then do in the merging stage is then I will really form out of all these well-formed trees that are grouped together, I will form a well-formed tree. Yeah, so of course here it might not make a difference so far because they are already in balanced mode. So it might even happen to be the same edges as the local edges, but that doesn't have to be. And the root of every tree is the node of highest ID. Yeah? Here it's 6, here it's 10, here it's 9. Then again, they are checking, okay, with which edge they should group. And here, like this tree, for example, up here with root 6 has ID 6. And it sees that there's a neighboring tree of ID 10 and of 9. But 10 has a higher ID, so it tries to connect to the tree of ID 10. And for the tree with ID 9, of course, it also decides to connect to the tree of ID 10. You know, then they group together to a single tree, and that's about it. Okay. Now let's move into the details. What's really happening in order to realize all of this efficiently? So we are in the grouping stage. Yeah, and here this red one is this tree, right? So the red edges might deviate from the blue edges, right? So I just drew a tree here that is a well-formed tree of that component of nodes, yeah? And now, first of all, each node in this well-formed tree T asks its local neighbors, right? So the neighbors with respect to the blue edges, the local edges, for their tree ID, right, that they belong to. And so, for example, the neighbors of V say, okay, I belong to the tree with ID 3, the other one says, I belong to the tree of the ID 10, and so on. Yeah, and what each node does, it just goes for the maximum of the tree IDs reported by its neighbors. Right, so this node V goes for 10, this for 7, this for 4, and then what happens is that there will be a so-called converge cast upwards towards the root, yeah, telling the root, okay, what is the neighboring tree of maximum ID? Yeah, and since this is a well-formed tree, the root can be informed in a logarithmic number of rounds, obviously, yeah, because so the leaves of this tree start will send their maximum, you know, to their parents, then the parents know everything, the maximum of their subtree, and then they send the maximum upwards and so on. So the leaves here, 10, like with the information 10 and 7, for example, they reported to the node that knows 8 so far. Then the node can compute the maximum of its subtrees and its own ID, which then results in 10. This will also be reported upwards, and at the end, the root knows the maximum ID of a neighboring tree over all of the neighboring trees. So the root can now send this information downwards again, so that all the nodes are informed about the maximum tree ID. And of course, this can also then be done in a logarithmic number of rounds. Just some side remark. Of course, the nodes only need to consider tree IDs different from their own tree ID. So for example, if this node somehow discovers that the neighbor of it already belongs to its own well-formed tree, of course, it doesn't need to report that, right? Of course. They should only report IDs of trees that are differing from their own tree, yeah? And if no IDs of other trees can be found in the neighborhood of any node of this global tree, then of course all the nodes in the system already form a single global tree and we are done. Yeah, so that's also an easy way how you can check termination. Yeah, if none of the neighbors says to the root, you know, I still found a different, like an idea of a different tree. If none of them say that, then obviously, you know, we just have a single global tree left, a single well-formed tree left. So the whole thing can terminate. Okay. Oh, and just one small detail, together with the maximum tree ID, also the node of maximum ID in T that reported that tree ID is determined in this converge cast, because it might happen that the tree of maximum ID, here in this case 10, has two neighbors in this tree, and then two nodes are reporting that they are connected to a neighboring tree of label 10, and then there might be confusion on which of the nodes should be chosen for the grouping edge. To avoid that confusion, in this converge cast, also the node of maximum ID in the tree that reported this 10 here will be determined. Yeah? So that a unique node in the tree can be determined who then is supposed to establish this grouping edge to this neighboring tree of maximum ID. It's just a detail, yeah, a small detail. Okay, so as I said, then this maximum ID of a neighboring tree will be reported downwards again. That also just takes the logarithmic number of rounds. And then the grouping edge can be established. Yeah. Because this node now knows for sure I'm the one that is supposed to establish this grouping edge. If, of course, this is non-redundant. But if all the nodes are informed about the max ID, and I also assume that this happens for the neighboring trees, then I can easily check for redundancy. So that these things can always easily be resolved because, you know, for example, if this tree has a larger ID than 10, yeah, and this node wants to connect here, because the other node that belongs to 10 will also know whether there's a node supposed to connect to this tree, yeah, that wants to connect to 10. So basically, every node then knows what's happening, what kind of connection the other node in the tree wants to do, so that they can locally check whether a connection is redundant or not, and if they figure out that a connection is redundant, then they don't establish it. So that really there's just one incoming, one outgoing edge, and whenever an outgoing edge is established, then there's no incoming edge from the same tree. This can easily be done. Now the only thing that you have to do is, if the grouping edge was indeed established, that you have to now root this tree. Yeah, because you want to make sure that you know in which direction to connect, so that you connect upwards towards the new root of the new tree that is established by merging all these trees together. And the directions of the edges, the orientations of the edges should all go towards this grouping edge which is established. Yeah? And so that requires another kind of communication upwards to the root, because the node down here that established the grouping edge has to tell the group, yeah, I really established this grouping edge because there was no redundancy. And then the root just tells everybody, okay, this is now your new direction or orientation for the edges, so that I establish a rooted tree again. Yeah? Okay, that's the basic idea. So that at the end of the grouping stage, I basically have lots of rooted trees. I merged these well-formed trees into large rooted trees that even have a constant degree, because I also maintain this property. Oh, sorry, no, I can come to that later. They have constant degree apart from the grouping edges. They represent some complication. But we'll deal with that in the merging stage. You will see that later. But the tree is already rooted, so that's important. So at the end of the grouping stage, we already merge trees together, so that again we have rooted trees afterwards. Okay. Yeah, this is just the information that the root makes sure that all the edges are oriented towards the grouping edge that is established.
Quick question.
Yeah.
Maybe you mentioned it already, but cycles cannot form because the IDs are...
Yep, yeah, that's exactly the lemma I'm going to show now, that no cycles are formed. Yeah, the grouping edges do not create cycles of global edges. And of course, cycle between two trees cannot happen because I already do this redundancy check, between two trees. So if both trees want to connect to each other, then the one with lower ID wins. Yeah? Okay, that is that part. So the only interesting part that's left is that you have a cycle via more than two trees. If you have a cycle via more than two trees, obviously you can't have a situation that you always have an edge from a tree of lower ID to a higher ID. That's impossible because this cannot happen in a cyclic fashion. So therefore, there must be a situation where the ID also goes down, where like the ID of Ti is larger than the ID of Ti plus 1. But due to our grouping rule, it cannot happen that ID of Ti minus 1 is larger than ID of Ti, and this is also larger than ID of Ti plus 1, because otherwise Ti would have connected to Ti minus 1 and not to Ti plus 1. Yeah? So therefore, two largers in a row, larger thans in a row can't happen. Yeah? And in fact, whenever this happens, what we also know is whenever we have that situation that ID of Ti minus 1 is less than ID of Ti, and this is larger than ID of Ti plus 1, in this case, the ID of Ti minus 1 must also be strictly less than the ID of Ti plus 1. Why? Can anyone tell me why between these Ti minus 1s and Ti plus 1s, I must have this strictly less requirement? Because if this is not the case, then Ti would again connect to Ti minus 1. Right? The only reason why Ti preferred Ti plus 1 instead of Ti minus 1 was that the ID of Ti plus 1 was larger, right, than Ti minus 1. So obviously, whenever I have such a scenario, we must have the situation that ID of Ti minus 1 is strictly less than ID of Ti plus 1. Yeah? And now, removing all such Ti's and in some sense directly connecting Ti minus 1 with Ti plus 1 gives again a cyclic situations of larger than relationships, and this can't be. Right? So it's definitely, the cycles cannot occur. Yeah? So that's the proof. So therefore, we are safe. Okay. So let's summarize what we did in the grouping stage. So first, every node locally determined the maximum tree ID of the local neighbors. Yeah? This just takes two communication routes. Yeah? Like one question, one answer back. Then, the maximum ID of a neighboring tree needs to be determined. This is done via a converge cast towards a root. This takes a logarithmic number of rounds. Then the root needs to inform all nodes of the tree of the maximum tree ID that the tree wants to connect to. Also just takes a logarithmic number of rounds. The check whether the connection is redundant. So a node needs to double check whether this connection is redundant for the grouping edge that it wants to establish. Also just takes two communication rounds. And then we need to route the tree in the direction of the grouping edge. If it is established, this just takes a logarithmic rounds again. So in summary, the grouping stage just takes a logarithmic number of rounds. That's good. Now, the merging stage. Now we are already at a point where, as I said, where the whole tree that is now formed via this new grouping edges, this is now a single rooted tree, but the degree might be too large. Because remember that these grouping edges are established on top of local edges. And the degree of the local network can be arbitrarily high. And so we definitely have two violations. One is that the degree of this global tree is simply too large. And the other one, of course, is that the diameter might be quite large. Because we might glue lots of global trees together via these global edges, via these grouping edges. So we have to do something about it. Okay. What do we do? To get rid of this high degree, that is really easy. I just transform this tree into a sibling tree, which means that for all of these grouping edges, I just transform them into a sibling list. So basically, all these neighbors that are children, like starting points of grouping edges, they inform the endpoint of these grouping edges, hey, I want to connect to you. I mean, this is already done in the grouping stage. And now this node V, of course, can check whether the degree became too high. And if so, it just can introduce in one single communication round all of the children to this children list. And this is doable because for that, it can use the local edges. And for the local edges, we have edge capacities, right? So the node can communicate over all of the local edges in parallel. Because for that, we are using the congest model, standard congest model. So there's no node limitation here. We only have edge limitations. So the node can do the transformation into the sibling list in just one communication round. And we are back to constant degree, global rooted tree. Yes?
But in a later step, can you have not local edges anymore? Because
No.
you already did the transformation and used
No. It's always because the grouping edges are always established via local edges. Because you always check your local neighborhood for a neighboring tree that you want to connect with. And so a grouping edge will always be formed over a local edge, yes. So you never run into this problem. Yeah? So therefore, you can always do this transformation into a sibling tree. You're back to a constant degree tree that is rooted, And the nice thing is, the only problematic thing is that it might have an arbitrarily high diameter, but we already know how to handle these things. Because there's a single root left. Because all the other trees, they oriented their edges towards these grouping edges. And then the roots also gave up. The root property, of course, there's just a single root left. So it's a rooted tree of constant degree, but the diameter is arbitrary. However, we can just use the transformation I told you about before, and we are done. Just Euler tool, right? Via shortcuts, establish then a list of nodes, doing shortcuts on the list, and carve out a tree from these shortcuts. Binary tree. It's as easy as that. And here I just say, to obtain sibling tree, just introduces its children, which is easy because it's via local edges. Okay. And as I said, we are back then to the rooted tree case, where the rooted tree already has constant degree, so we know how to handle that. Great. So what's the runtime of the merging stage? To transform the rooted trees resulting from the grouping stage into sibling trees can be done in one communication round, because each node can just knows from the grouping stage how many nodes in the local network want to establish connections to it via grouping edges, so it can just do this transformation in one round to this child list. And then to transform the rooted trees into a well-formed tree, again, just takes O of log n rounds, because we already saw how to do it. So altogether, the merging stage also just takes the logarithmic number of rounds. In summary, this means that the well-formed tree problem can be solved in log n squared rounds, because each grouping at merging stage just takes the logarithmic number of rounds. After each grouping and merging stage, the number of well-formed trees has definitely reduced by a factor of at least 2, because every tree, of course, will connect to at least one other tree. So it goes down by at least a factor of 2. Sometimes even more dramatically, as you could see in the examples. So therefore, after log n rounds of, running log n rounds for log n times, we are done. So it's log n squared. GST now should be well-formed tree algorithm. Global spanning tree, I called it, like way back in time. And the nice thing is, for that algorithm, the nodes do not need to know n. They never need to know n. Termination is just achieved by checking in the grouping stage whether there are neighboring well-formed trees left. And also for the shortcutting and so on, the nodes will observe naturally that the shortcutting is over, so that they can proceed. So knowledge of n is not needed. So it can basically start in a situation where all that each node knows is its local neighborhood, and that's it. That is totally sufficient for the algorithm to run. Yeah, simple applications, of course, is now you can easily collect statistics, yeah, about your local network. You can easily, for example, compute the number of nodes in the local network. You can easily also compute the number of local edges because it's just an aggregation along the well-formed tree, yeah, and that's it. So you can easily collect statistics. Yeah, in general, right, if, for example, your local network is a mobile ad hoc network, yeah, which is one of the examples that we specifically looked at also, yeah, so then the global connections would be via the cellular infrastructure, for example. Yeah, then once you have a well-formed tree on top of that wireless network, you can collect lots of statistics, and I will also show you how to make use of it, for example, in this context of shortest paths, so that you can compute shortest paths in wireless networks, in wireless ad hoc networks much faster than if you would just use the wireless ad hoc connections. Yeah, but first let's stick with some basic graph problems. The next one is minimum spanning trees. By the way, how I'm doing time-wise? Everything is fine so far?
35 minutes
Oh,
for this block.
great, okay. Yeah.
You're just concerned about constructing trees now. Can you explain why this is? Are there no other data structures that would be interesting similarly, or is this not? Is this clear they don't exist, or are too complicated to handle? Or?
Again, that's actually the same reason why I just went for the synchronous message passing model.
Yeah.
The tree is the most simple network you can come up with for which you can perform operations in a scalable manner, because it just has a logarithmic diameter.
Yeah.
Yeah, and so already when it comes to collecting statistics, the tree is good enough. Of course, when it comes to exchanging information, right, like you have like a routing problem where you have multiple source destination pairs, then a tree is not a good idea. Why? Why is a tree not a good idea if you have like multiple source destination pairs? Because you have a bottleneck at the root, right? Most likely a lot of messages have to be sent over the root, and then you have a bottleneck. Because remember, we have node capacities for the global edges, right? So irrespective of the number of connections the root might have, it can only send polylogarithmic amount of bits per route. So definitely that's not enough in order to serve, let's say, theta of n source destination pairs. Yeah, so for routing tasks, this is not a good idea to have a tree. There are other networks like butterflies, hypercubes, and so on. You might have heard about these. In fact, I will talk about hypercubic networks later also in my presentation. But a tree is good enough as a starting point for many things, because once you have a tree, it's also relatively easy to construct other networks from that in a logarithmic number of communication routes. Yeah? So that's why I used the tree. It's kind of a core structure, even though I should also mention that, of course, the tree is also a most fragile structure. Even if you want to use it as an intermediate structure, in reality, it's not a good idea. So I should use a disclaimer here. So don't use the strategy as it is for real applications, because first going for a tree as an intermediate structure and then going for your network that you want to have, it's not a good idea, because if the root fails, then you're in trouble, right? So, so therefore, this is theory, right? This is the first step. This is just introduction to the field. Don't use this directly in your application areas. If you are busy there, of course, talk to me how to do the real thing, right? Because there are lots of other strategies that you can use, much more advanced strategies that avoid the use of trees. Anyway, so again, just trees. Next thing is still a tree, but as I said, forget about fault tolerance issues for now. Like, we are also completely ignoring faulty nodes, Byzantine nodes, you know. We assume that they are not existing. Spanning trees. Let's not go for a minimum spanning tree. Let's just talk about the spanning tree for now. So all we want to do is the following. So we have a hybrid graph H equals VLE, where V comma L is connected. Yeah, it's, of course, we need connectivity to establish a spanning tree on top of the local network. The set of global edges is initially empty. And at the end, what we want to have is a spanning tree of the local network. If you want to do it with a sequential algorithm, definitely you need a linear runtime. Yeah? If you want to do it in a distributed fashion, if you just have the local network available, the best you can do is O of diameter many steps. Yeah? So there are lower bounds that you can't avoid if you don't use the global edges. Yeah, and they are pretty high. So what can you do if you have a hybrid network? So you have global edges. Run your well-formed tree algorithm, yeah, so that you form this well-formed tree, and on the way of forming the well-formed tree, you mark all edges in the among the local edges that are used for grouping edges. And I claim that the union of the marked edges is a spanning tree. Why? So we are done. When we mark the grouping edges, we form a spanning tree. The marked edges form a spanning tree of the local network. Because the invariant that we can maintain is that for every well-formed tree that we have already formed, the grouping edges needed in order to form it are a spanning tree of the nodes that are forming this well-formed tree. This is basically the invariant that we preserve throughout the algorithm. We can prove that we really can maintain this invariant. Yeah? So that the grouping edges, if we just mark them, are already giving us a local spanning tree. That's easy. Yeah, so correctness, as I said, by induction, it's just an inductive proof. Yeah? It can be shown that for each well-formed tree T during the construction, the grouping edges used for forming T represent a spanning tree of its node set. Yeah? That's what we can maintain, and it's really an elementary proof. So, in order to compute a spanning tree, an arbitrary spanning tree on top of a local network with the help of global edges can be done in log n squared time. Okay, what about the minimum spanning tree problem? Yeah, so given a hybrid graph, H equals VLE, where VL is connected and E is initially empty, and now we have some, arbitrary edge weight function, yeah, that assigns natural numbers as edge weights to all of these edges. Compute a minimum spanning tree. Yeah, we call Kruskals algorithm or Berufkas algorithm, right? Whoever you want to call it. So start with all nodes in V representing their own minimum spanning tree, and then we repeatedly look for an edge E of minimum weight whose endpoints belong to different minimum spanning trees of their node sets, and merge these two minimum spanning trees into one minimum spanning tree of the combined node set by adding that edge until all minimum spanning trees have been merged into one. Yeah, that's the idea. The only difference is that in the standard Kruskal algorithm, you do it sequentially. Yeah, you sort the edges, and then you look at these edges in the order of their weights, and whenever you find an edge connecting different minimum spanning trees, then you add it to the minimum spanning tree that you want to establish, right? And otherwise you just throw it away. So here we want to do it in parallel, of course, because we want to get full parallelism. So here's just a simple example. This is just revisiting Kruskal's algorithm. So it does it sequentially. It just sorts the edges of lowest weight are 1. So it first connects these two nodes to form a minimum spanning tree. Then there's another edge of weight 1 that can be added so that these two nodes also form a minimum spanning tree. Then the next lowest edge weight is 2. So we can establish these nodes into a minimum spanning tree. Then here's another edge of weight 2, and so on. And basically this is the tree that you get, right? All these red edges, they basically form the minimum spanning tree that you get from Kruskal's algorithm. Okay. We need one assumption if we want to do it in parallel, because we need to assume that the weights of the edges are pairwise distinct. Otherwise, you can create cyclic relationships. So every edge has a unique weight, which of course can easily be established even if the edge weights are not distinct, because you can always, as a tiebreaker, use the binary encodings of the IDs of the nodes. Yeah? You just append them as lower order bits to the edge weights. And since the nodes have unique IDs, you can then make the edge weights unique as well. Yeah, so that is a very simple trick. So here we really need the fact that the nodes have distinct IDs. Yeah, and then we can use a parallel variant of Kruskals algorithm. Yeah, we start with all nodes in V representing their own minimum spanning tree. And as long as there are at least 2 minimum spanning trees doing parallel for each MST, look for an edge of minimum weight, leaving that minimum spanning tree and add it to the set of MST edges, which causes then the MSTs to merge. And an easy lemma that can be shown is that if all edges have distinct weights, then the parallel variant of Kruskals algorithm will never create cycles of MST edges, which is relatively easy because for 2 MSTs, I mean, there cannot be a cycle because it must be the same edge, right? If they agree that the edge of minimum weight is really like establishing a connection between each other, yeah, so that T1 has no other edge of lower weight and T2 also has no other edge of lower weight. Since this weight is unique for each edge, there's a unique edge via which they will connect, yeah, to a larger minimum spanning tree. So therefore, there's definitely no cycle appearing here. So it must be the same edge, as I said, that's easy. And of course, we can't have a cyclic situation for a larger collection of trees, because note that if T2 does not go for the edge of weight C1, but for an edge of C2, then since the edge weights are unique, C2 must be strictly less than C1. Yeah? So we definitely have the situation that Ci is larger than Ci plus 1 for every I. And therefore, we would have to have a cyclic situation of this larger one relationship, and that can't be true. So therefore, definitely we can't establish cycles. Yeah? So also here, the trees will just in parallel merge to larger trees, into larger trees. That's also very easy. So we are safe here as well. So now, how do we establish a minimum spanning tree? We can just do it via an adapted form of the weight of the well-formed tree algorithm. Yeah, the adaptation is really minor. Can you imagine what the adaptation is? For the grouping edge, that's the only thing where it differs. Not the only thing, there are also some minor other things that you have to worry about. But for the grouping edge, you now do not go anymore for the neighboring tree of maximum ID. You now just go for the edge of lowest weight connecting your tree to a different tree. That's it, yeah? So in the grouping stage, instead of looking for a neighboring well-formed tree of highest ID, the edge of minimum weight to another well-formed tree is selected. Trees are reoriented as before, which means in the direction of the grouping edge. Yeah? And because of the previous lemma, we know that, again, this wouldn't create cycles. Yeah, merging stage is as before. So we wouldn't have to worry about it here. And because this adapted well-formed tree algorithm behaves exactly as the parallel variant of Kruskals algorithm, yeah, so it also, of course, then computes a minimum spanning tree. So therefore, also minimum spanning trees can be done in log n squared time. Yeah, which is summarized in this theory. This is also good news. Shortest paths. Yeah.
Maybe it's nice to note that for minimum spanning trees, you don't need the local edges. I mean, for your algorithm, you need it. It makes it much easier, but we have an algorithm which just uses the global.
Yeah, the only tricky thing is if the degree of the local network is too high.
Oh, we have the
yes. Yes, that is our, that's true. That's a good remark. Right, we have this paper where we assume that in some sense the global edges form a clique. And indeed, the minimum spanning tree can even be solved exactly for arbitrary local networks just by making use of the global edges, yes. With this limitation right on the node side. That's good enough. Indeed, I haven't also talked about some other things because I said that the well-formed tree part, this needs log n squared rounds in order to form. Of course, you might ask, what's the limit? A natural lower bound is log n. Yeah, there's nothing, you can't surpass log n. You can't be better than you can't have a runtime that's below log n. Simply because the best you can do with global edges is reduce the diameter of a given network by a factor of 2 in each round. yeah, via this shortcutting approach. That's the best you can do. Information can't travel faster than that by using this shortcutting approach, this pointer doubling. If the diameter of the original network is n, basically, and you start with an empty set of global edges, then you definitely need a logarithmic number of rounds. There's nothing you can do about it. So, of course, a big question has been, how close can you get to this log n? The first improvement that we made is that we got down from log n squared to log n to the power of 3/2 by just using even more parallelism that we already have. In a sense that you establish connections to lots of trees much more aggressively in some sense. Because you're not really exploiting full parallelism. In some sense, what you do in the single tree is always like a converge cast and broadcast, and like lots of nodes are not doing anything. And if you like let all the nodes do much more things, that you explore larger neighborhoods basically of the tree setting, then you can speed it up by a squared of log n factor. And then if you use like heavy machinery using random walks on these local networks and so on, you can even go down to log n. So there's a paper now showing also that you can do this waveform tree formation in O of log n time, which is exactly at the limit of what you can do. But this is using like heavy machinery, and if you're interested, definitely ask me and I will point you to the corresponding paper. And I do have a list of references also at the end of the presentation. Yeah, so it's really just an introduction, yes, and the heavyweight stuff is postponed. Shortest path. Now, what I want to solve is let's assume just the single source shortest path problem. Yeah? So given a hybrid graph H equals VLE, where VL is connected and E is initially empty, a node S, and a length function C, yeah, that associates some length value for each local edge, compute the distance d of V of every node V to S in the local network. Yeah? Of course, again, if you just have the local network available for you, then the best you can do is you need the diameter of the local network many communication routes. Yeah. In fact, is there a better lower bound? I forgot for SSSP in the local network. Lower bound. Is there a better lower bound than the diameter of the network for SSSP? Like the expert, I guess Fabian or so. Maybe you know a better lower bound or so. I'm not aware of it. Yeah, congest model for the general graphs. Yeah, d plus square root of n. Yeah, I wasn't sure again whether this is valid for the SSSP. Okay. Okay, so it's d plus square root of n. I wasn't sure before I say something here that's wrong. Just wanted to reconfirm. So therefore, like the lower bound is even square root of n. Yeah, so for the local network, it's really expensive to do it if you really just have the local network available. So here in this introductory lecture, I'm really also just focusing on special cases of local graphs. So I'm not going into these like full-scale general constructions just to keep things simple. So let's just look at specific cases of local graphs. And because I didn't also push it further for my master's level course. So let's start with the list distance problem. Yeah, given a hybrid graph H equals VLE, where VL is an undirected list and E is initially empty, we have a node S and edge lengths given by C. Compute the distance d of V of every node V to S in V, L. Yeah, and of course the naive solution via just some breadth first search, you know, it's too small, obviously too slow. So again, of course, pointer doubling. Yeah, we can make use of pointer doubling. So all the nodes do it in parallel. Yeah, starting with the lowest level, yeah, which are the local edges. The nodes create shortcuts of higher and higher levels until no further shortcuts can be constructed. And for each shortcut E, created for edges E1 and E2. The length of E is just the sum of the lengths of the two edges, yeah, that result in the shortcut, so that you keep track of what total length you are bridging here, right? And that results in these edges shown here in this picture. Yeah, and once you have that, then you just again perform something that's looks similar to like a parallel binary search from the source node S. Yeah, but here in a slightly different way than we did for this binary tree construction, because now we are just going away from S. So what we do is, as I said, we start from S and yeah, only move away from S, never towards S. And we start with the largest level shortcut to the left and to the right from S. So we first use just this one highest level shortcut from S to the rightmost node here that has a length of 7. Yeah, and then we successively go down edge by level by level. Yeah, the next level is the next edges used by S are then those edges with distances 4 and 3. Yeah, and it informs the corresponding endpoints that their distance to S is, you know, for the left endpoint it's 4, for the right endpoint it's 3. And it just goes down from there. And once a node has been visited by a level I edge, then it uses its level I minus 1 edges to inform its nodes, yeah? How to, what their distance to S is. Okay, so since this approach just it's able to traverse the entire graph in just a logarithmic number of time, this means that the list distance problem can be solved in O of log n time. Yeah, so that is particularly easy. Let's again look at the tree. Let's also look at the tree. So given a hybrid graph H equals VLE, where VL is an undirected tree T, and E is empty, a node S and edge length C, compute the distance D of V of every node V to S in V, L. Of course, the only problem is the tree might have a large depth. Oh, that's one problem. The tree might have a large depth. As it will turn out, we can efficiently solve the tree distance problem if tree is rooted towards S, but initially that might not be the case. So let's first look at the problem of getting the tree rooted. Yeah, so this is the so-called rooted tree problem. So given a hybrid graph H equals VLE, where VL is an undirected tree T, the set of global edges is initially empty as always, a node S, turn T into a rooted tree with respect to S. So basically orient the local edges so that every node knows what is its parent and what are the children with respect to S. Because once we have a rooted tree, things get particularly easy. So we want to have a rooted tree. If the tree has constant degree, of course, it's easy. Because then we can again establish an Euler tour. Yeah, and an Euler tour basically can also be established if the nodes do not know who's the parent and which are the children with respect to S. Yeah, they just have to come up with some ordering of their nodes. Yeah, whatever ordering they choose, that's good enough. Yeah, so basically a node, if it has basically one parent and 3 children, it creates 4 virtual nodes again, and then it just establishes a tour through its virtual nodes in a kind of a round-robin fashion. And that's good enough to establish an Euler tour. Yeah, so if the degree is constant, then every node only has to emulate a constant number of virtual nodes, so everything is fine. So we can easily establish such an Euler tour without requiring the fact that the tree is rooted. Yeah, so here's the general construction. Yeah, if a node has 4 neighbors, then it just decides to, for some round-robin strategy, it just orders the neighbors in an arbitrary way, and then locally connects them in this particular fashion, and that's it. And this will always result in a single round trip through the tree. Simple exercise. Yeah, and since the node S knows it's supposed to be the root of the tree, of course it's easy to break that cycle. Yeah? So that we now get a list with lots of virtual nodes in this list. yeah, where the node 1 appears 4 times as a virtual node. And now we do the following. We apply the solution to the list distance problem. How many? 10? Okay. So we apply the solution to the list distance problem to compute the distance to the from S from S prime. So basically that's the initial, like this is the virtual node that S starts with, right? So S basically chooses one of its virtual nodes as the starting point. And that's it, right? This is the so-called node S prime. And we use this algorithm, as I said, the list distance algorithm, to compute now the distance of all of these virtual nodes to S prime. And let now V prime be the first virtual node of some node V that is, or the virtual node that is closest to S prime, yeah, with respect to the distance computation. Then the predecessor of V prime is the virtual node belonging to the parent of V in a tree rooted at S. Why is this the case? Can you imagine this? Why indeed a node just has to check the distances of all of its virtual nodes, and whichever of its virtual nodes has the smallest distance, if it just goes for the predecessor, then that must be the parent of it in the tree. Is this clear? Yeah, because if we go back to this picture here, it's probably more easy to see, right? The node here, the node number 1 that has these 4 virtual nodes, it has no clue in which order these virtual nodes are visited from the starting point of S, right? But whatever this virtual node is that is first visited, the node right before it, right before it, is actually its parent. Yeah? That's the interesting thing. And you can easily check it for all of these nodes, right? That this is really true. Okay. So in fact here, the parent of 2, 3, and 4 is, for example, 1, because their predecessor is node 1. And indeed, if we look at this original picture, here 2, 3, and 4, the parent node is 1, yeah? Well, here it's particularly easy because it's just leaves, yeah, but okay. Yeah, so it's basically a simple list distance problem that we need to solve to figure out what is the predecessor. So therefore, if the tree T has a constant degree, we can root it in O of log n rounds. What if it has an arbitrary degree? Then it gets more tricky, because then a node might have to simulate many virtual nodes, and then we can't use this list distance approach anymore, because then the limitation is that the node can only handle a polylogarithmic number of messages in each round, yeah? And that is not enough so that it can let all of its virtual nodes participate in this list distance approach. So that's not going to fly, so we have to do something about it. Yeah, so maybe the idea is maybe we can distribute the virtual nodes so that each real node has to simulate just a constant number of virtual nodes. And I guess some people in this room already know what kind of techniques works here. Nash-Williams forest decomposition works here. Yeah, and this really allows the virtual nodes to be distributed among the real nodes so that every real node only has to emulate a constant number of virtual nodes, so that we are back to the nice case. Yeah? That we can run this list distance approach. How do we do that? For that, first I need to introduce the arboricity of a graph. The arboricity of an undirected graph G is the minimum number of forests needed to cover all edges of G. Here in this graph, you see that 2 forests suffice to cover all edges in G, right? You see this blue forest and the red forest. Yeah, 2 forests are sufficient, so therefore the arboricity of this graph is 2. obviously, as can be seen from the picture. Okay, what's the arboricity of a tree? That's particularly simple, right? It's 1. Okay, and we started with the tree, right? I mean, the only thing we worried about was its degree, right? But the tree has an arboricity of 1, and we see why this is really useful. Okay, so what does the Nash-Williams forest decomposition do first in a very, very simplified form? So I have a simple repeat loop, and in this repeat loop, I repeatedly remove all nodes of remaining degree less than 4 times the arboricity of G. And let's assume that the nodes know the arboricity of G. Yeah? So they know this threshold 4 times the arboricity of G, so they can locally determine whether they are now down to a degree of less than 4 times A of G. And if so, they remove themselves and all of their edges as well and notify their neighbors about that, yeah? Until all nodes are removed. I claim that this repeat loop only needs a logarithmic number of rounds. Why is this true? First of all, some statement like if I take a graph and this has an arboricity of A and I take any subgraph induced by a subset U of V, then of course it must also have an arboricity of at most A. I mean, this is simple, right? If I restrict the set of edges to a subset, then the arboricity won't grow, right? At best it can shrink. Okay. And now imagine you have a graph of size n and arboricity A. Well, how many edges can it have? Because remember, you have to decompose it into these at most A many forests, and a forest can have only n-1 edges, obviously, right? Because otherwise you have a cycle. So definitely in total you have at most A times n-1 edges in such a graph. And thus at most n/2 nodes can have a degree of at least 4A, because otherwise the whole degree is eaten up, right? Because n/2 times 4A is 2 times A times n, and here we would count every edge twice, so we would have to, divide by 2, and then we are back at A times n edges, but this is too much, because we only have A times n-1 edges, right? So definitely there can be at most n/2 edges of degree at least 4A, right? So therefore, in every round we will get rid of at least n/2 nodes. 2, 3, no? Okay. Yeah, I will finish this up with a Nash forest decomposition, and then that's it. Okay. So now I slightly beef it up the algorithm. I do something on top of just removing these nodes. So what I also do is I oriented all remaining edges of V. So whenever for every node V, yeah, that has a small enough degree, I oriented all remaining edges of V from V to each of its neighbors, unless that neighbor has a lower ID and also degree less than 4A of G, and then I remove V and its edges from G. Right? So there's some tie-breaking rule because I don't want to have some cyclic relationships, right? If 2 nodes want to drop themselves from the graph at the same round, then the tiebreaker is, whoever has the lower degree is allowed to connect to the other node, yeah, and then we are fine. Now, what I can say about this is that this Nash-Williams forest decomposition always transforms G into a directed acyclic graph of out degree at most 4 times A of G. Yeah? Can you imagine why it's acyclic? Because nodes can only have edges from a prior round to the next round. Right? Because otherwise this edge would have already been removed from the other endpoint. Yeah? So if an edge still exists at round R, then it means that the other endpoint hasn't removed it yet. Yeah? So it's also still existing. Right? And so the only thing that can happen is that 2 nodes vanish at the same time, but then there's this ID tiebreaker that makes sure that edges are just going in one direction. And you see that definitely it must form the edges, if the orientations of the edges must form a DAG. Yeah? Of out degree at most 4 times A of G. And this DAG now will be particularly useful for the simulation of virtual nodes by the real nodes, in our case. Can you imagine, that's the last question, then we are up for a break. Can you imagine how we can make use of this fact to distribute the responsibilities for the virtual nodes among the real nodes so that every real node just needs to take care of constant number of virtual nodes? Question to the PhD students. So did you follow it? Remember, we have a tree, right? A tree of possibly arbitrarily large degree. And so what was the aberricity again of that tree? It was 1, right? So therefore, it's totally fine if every node just emulates, 3 would already be sufficient, right? Because if it's less than 4 times AG, like it's less than 4, so if it has a degree of 3, it can already then stop and basically do the emulation. Oh, well, it has to emulate itself as well, possibly, yeah. So it's maybe 4. Okay, 4, but that's it, right? A node only has to emulate 4 other nodes, and that's it. 4 other virtual nodes in some sense. Okay, let's stop at this point. And we'll continue after the break. The edges of each color must form a tree because the graph established by these edges, as I said, is a directed acyclic graph. And actually, you can't have a cyclic relationship between these edges. Okay. So our strategy for the rooted tree problem, to sum it up, is each node simulates all edges of the Euler tour that correspond to its outgoing edges of the Nash-William forest decomposition so that the virtual nodes can be nicely distributed among the nodes. Yeah? Oh yeah, I say that here. Every node will only take care of at most 3 edges, which means that it has to simulate at most 6 virtual nodes actually. Or actually, at most, 6 edges, also 6 directed edges, and this also means 6 virtual nodes. Yeah, so the rooted tree problem can therefore be solved in logarithmic time. Now, let's come to the tree distance problem. Yeah, so we want to compute distances from a source node S to all nodes. And now we have an arbitrary undirected tree T, that is not rooted initially, that can have an arbitrary degree. But now we have all the tools that we need in order to solve the general tree case. The strategy works as follows. We first turn T into a rooted tree. We already know how to do that in a logarithmic number of rounds. Once we have a rooted tree, we can easily transform it into a constant degree sibling tree. Because once it's rooted, every node knows what is its parent, with respect to that tree, and or rooted by this node S. And what are its children? And what it simply does is it establishes a child list among its children. In that way, we get the same benefit as we got for the sibling tree when we looked at the grouping stage. Because each node will just have one parent, but it might have many, many children. So if I can convert the children connections into a sibling list, then I immediately lower the degree to at most 2, right? So you still need to connect to one parent and to one child of your child list. Oh, sorry, and each child also has to remember the left and the right sibling, so these 2 come on top of it. Possibly, so there are 4. There are 3. I think 3, yeah. In the worst case, a node has to take care of its 2 siblings and the child for the next lower level. So the degree is at most 3. Yeah, and of course, when doing this, when transforming a tree T into a sibling tree, I just have to make sure that I preserve distances in that way. So that we can still, if we want to solve the tree distance problem in this sibling tree, we still get the correct distances with respect to the original tree. But you can imagine that there's a fairly simple strategy. In fact, here it suffices that S, for example, sets the length of the edge from U to V to 3 and the length of the edge from V to W to -1. And then you can easily check that the distance from S to V and the distance from S to W is the same as before. Yeah, so you can check it that the distance from S to V still is at 4 and the distance from S to W is at -1. And the simple solution that you can do for that in order to get that result is that you just take the differences of the edge lengths for the corresponding child edges, yeah? So that they cancel each other out. Because what you get in this case is if you take the differences of the first two children and the differences of the second two children, yeah, the difference between the edge lengths of U and V and W, then for the distance to W, basically the distance to V cancels out, yeah, because at one point it's included in the positive form, in another formula it's included in the negative form. And then it cancels out, it basically gives you this telescoping sum, so that the distances of the nodes in between cancel out, so that all that remains is basically your distance to the source. That's the basic idea. So it works just by taking the difference of the edge lengths. So the general construction is really the following. Yeah? For each VW in T that is kept in T prime, of course, this parent edges that are kept in T prime, we just use the original distances. There's now no change here. And for each sibling pair, VW, yeah, where the edge goes from V to W, we just take the difference of the original edge lengths. Yeah? So C prime of VW, so the new distance, is just equal to C of, C prime VW is, U is, no, wait, here I did a mistake. Sorry, the parent node is U. Oh, okay. So don't look at the picture. So here in this case, we have a sibling pair VW where the parent node is U. So it's not the same as the picture here. So don't get confused by the picture. So here, U would have to be replaced by S, yeah? So what you really do is you take CVW is equal to C of SW minus C of SV. Yeah, because the parent of V and W in the picture is actually S. So just replace U by S and then you are fine. Yeah. And as I said, you just get this so-called telescoping sum where the intermediate distances cancel out so that all you keep is the distance between S and W. Yeah, so that is an easy exercise. So normally in the lecture I would then go with the students through that exercise. I don't know, are there any questions? Did I convince you? Otherwise I'll just move on. Okay, everybody seems to be happy. Yeah, so next I just transform T prime. Remember that after the transformation into a sibling tree I have a constant degree tree. So I can use the same trick as before. You see, like tricks, they re-emerge again and again. Yeah. So here and again, I just go through the tree in an Euler-Tour-like fashion. Yeah, and whenever I go in the direction of the edges, the original edge length is preserved. Whenever I go along the edge in the opposite direction, yeah, of its direction, then I basically subtract the corresponding weight. So that basically then an edge, for example, of length 3 from 1 to 2 is added whenever I am in this corresponding subtree, and once I leave that subtree, the length is subtracted again so that it doesn't matter anymore for the remaining nodes. Yeah? And when I do this very simple trick, when converting the tree into a line, then the distances in the line are actually the same as the distances in the original tree. Also that, I guess, can easily be checked. Yeah? Because in some sense, all edges that are not considered for the current path to the current node, yeah, that I'm considering, all of these edges are basically abstracted out so that they are irrelevant at that point. So if I consider, for example, this node of label 4, then only the edges with weights 1, 3, -1, and 3 are valid, yeah, of this unique path in the sibling tree reaching to that node 4. So this list approach makes sure that only these edges are counted, and all other edges that might exist, they have already been cancelled out again once I move backwards along that edge, because then I always take the negative length of that edge. Okay, so here's the simple rule, as I said. Yeah? In the direction of the edge, you take the original length, otherwise you take the negative length. Yeah, and it's relatively easy to see that the edge lengths preserve the distances in the sibling tree. Also, that is a simple proof that I skip here. So using our algorithm for the list distance problem now solves the tree distance problem. That's all. Okay, so in summary, the tree distance problem can be solved in a logarithmic number of rounds. Great. The question is, which other graphs allow the SSSP problem to be solved in O of log n rounds? I just mentioned 2 results here. So there's one result where we showed, okay, cactus graphs for them. We can also do it in O of log n rounds. So basically here, any 2 cycles share at most 1 node. Or there's a paper on so-called hole-free grid graphs, where you can also do it in a logarithmic number of rounds. And then there are more advanced papers that even look at the general SSSP result that can even do it in polylogarithmic number of rounds, but it's much more complicated, so that I skip them here. But basically, what you can do is you can, in some sense, this Nash-Williams decomposition trick is also very useful in general. Yeah? And you can play that strategy, for example, again, in certain contexts, or you construct so-called skeleton graphs in some given graphs, where you can basically come up with abstract representations of the original graphs, which gives you a much easier handle in order to compute shortest path values. But let me just skip that. Let me just look at the hole-free grid graph case. So what is the motivation to look at grid graphs? We observed that when you look at unit disk graphs, so unit disk graphs are graphs that people look at in this wireless networking context, where they say that 2 nodes in the wireless network that have a distance of at most 1, you connect them via some edge. And if you do that, whenever you connect 2 nodes of distance at most 1 by an edge, you get this so-called unit disk graph. And there is a nice abstraction of unit disk graphs. Basically, you can also represent them in the case where, let's say, the nodes have position information, yeah, which is normally the case if you think about our cell phones. Our cell phones know surprisingly well where we all are. Yeah, so if you exploit this distance information, then in some sense you can check which tiles in a certain area are basically covered, in the sense that there's a close-by node that could simulate routing along that tile. And then you can establish connections between tiles whenever there are like corresponding connections in the unit disk graph, like at the very high level. Yeah? So that you can come up with an abstraction of the unit disk graph as a grid graph, yeah? Which is just a subgraph of a 2-dimensional grid. And such a grid graph is hole-free if it doesn't have such an inner boundary as here. For example, this grid graph is not hole-free because it doesn't have just this outer boundary, but there's also an inner boundary here. So that grid graph wouldn't be hole-free. So I want to consider only grid graphs for now that are hole-free, because they make the situation much easier. Okay, so here is a hole-free grid graph. Yeah, so you see that this outer boundary goes in here, so that's not an inner boundary yet, because that boundary here inside is still connected to the outside world. Right? So that would be a valid hole-free grid graph. And what I want to do is I want to solve the SSSP problem for any given node S in this hole-free grid graph. The question is, how can I do it efficiently? The trick is, interestingly, I can reduce it to the tree case, yeah, which is not so obvious at first glance, but I will show you how. So what I do is I first construct the so-called vertical portal graph. First of all, what is a portal? a vertical portal is just a vertical line. It's like a contiguous sequence of nodes in the vertical direction. That is what I call a vertical portal. So all these nodes that are like all these connected components that form this red line, yeah, they are so-called portals. Yeah. So just at the moment I just established, I just basically partitioned these nodes into these vertical portals. Now, what do I do with these vertical portals? I choose a representative for each vertical portal, which is just the northernmost node of each portal. Yeah, that is easy. And now what I want to do is I want to connect these representatives of a portal with representatives of adjacent portals, yeah, that are either a portal to the left or to the right, which means, for example, that if I take the representative, for example, of the portal that includes S, you see that it has connections to two other representatives to the left, because they are representatives of adjacent portals. Yeah, you just have to go one step to the left in order to reach these portals, and one portal to the right. Yeah. So, and you do it now for all these representatives, and what you get is a tree. It might have a non-constant degree because there can be a non-constant number of adjacent portals on one side, but it's definitely a tree, right? Yeah, and certainly, first of all, to figure out the representatives, that is really easy because a node knows just by looking at its context, at its neighborhood, whether it is the representative of a portal or not. Yeah? Because it just needs to know whether it's the northernmost node, which it can locally check. So that's easy. Yeah, and all these other connections to move the information up to the portal, up the portal in some sense, or let's say for all the representatives to know representatives of adjacent portals, this can also be done in overflow and rounds, although there is a slight problem here again, because as I said, there is some non-constant degree that can potentially be the case here. But how can we deal with it when we have a non-constant degree? Can you imagine how we can still emulate this tree with global edges in an efficient manner if we have a tree with non-constant degree? I mean, in some sense, we can again make use of the Nash-Williams decomposition, right? To share the responsibilities, because again, it's really just a tree. And therefore, each node, again, the edges of the tree can be distributed among the nodes so that each node only has to take care of a constant number of edges of this tree. Yeah? And that is sufficient to, for example, emulate an Euler tour in the tree. Remember, right? Because we looked at this case before where we also had a tree of non-constant degree. So we can use the same trick here. Okay. So we can basically share responsibilities to emulate this representative tree. And this representative tree can be set up in overflow and rounds, yeah, by using this, making use of this Nash-Williams forest decomposition. Although it takes a bit work, of course, to figure out the details, yeah, because it's not so obvious anymore. I mean, a node has to collect its degree, but in some sense, you can imagine that you can do it easily by aggregation up these portals that a node knows about its original degree, and there are some tricky things where it has to keep track of the degree, yeah?
There's also a simple way to see this, kind of like you can take all the nodes on a vertical portal and just throw out most of the edges except one, which connects to neighboring portals, and then you have also a tree, but with all the nodes. But of course, this way you save some nodes, which might be beneficial.
Mm-hmm. Okay, and what you do is now you use the tree distance solution to solve the SSSP problem on the portal tree with source S prime, where S prime is the representative of the portal of S. Yeah? You just solve the tree distance problem as described before. for this portal tree. Okay. And now consider some node V somewhere in the system. Yeah, and let its representative V prime and consider this representative V prime of this node V, so that basically is the representative of V's portal. And so what V prime learns about is that its distance to S prime is 9. Yeah? So you can see actually that you have to do 9 hops along the tree in order to get from S prime to V prime. Now what each representative does is, after it knows the distance from S prime, is it informs all the nodes of its portal about its distance to S prime. Yeah, so that all the nodes know that with respect to the vertical portal tree, its distance to the source is 9. Yeah? Next, transform the grid graph into a horizontal portal graph. So now you just do it horizontally, the slicing. Yeah? Again, you define representatives for each portal, which are in this case the westernmost nodes. You again form the portal tree of these representatives. You compute distances. Yeah? And now, in this case, so V, the node was down here, right? So now the representative is this node V prime here, and it has a hop distance of the representative of S of 6. Can also be easily checked in this horizontal tree. Okay? And after this is done, so after all the representatives determined their distance to S prime, they again inform all the nodes of their portals. So the question is, how do you now get the distances in the grid graph to S? Any idea? You just add up the two distances. That's it. Yeah, of the vertical and the horizontal portal trees. It works because, so that would be a shortest path from S to V, and you can actually check that you have to do 9 vertical movements and 6 horizontal movements. Yeah?
Is it now relevant that we have a forest of 2 trees?
You mean for the Nash-Williams decomposition that I can...
No, because before we had the forest and we started to decompose it into the forest section.
No, it's not really...
Into trees, yeah?
I think the grid graph is just a very special case.
Yeah.
It's just a very special case because in some sense, each of these two portal trees, it captures really how many times you have to do a vertical movement and how many times you have to do a horizontal movement in this grid graph. Yeah, that's it. That's the whole story. It's not more to that. Yeah, so you can just decompose it into these two portal trees. So basically you can reduce it to the tree distance problem, and then you solve this hole-free grid graph case. Can you imagine why holes make a difference here? Yeah, it would not be a portal tree, right? So if you connect adjacent portals, you actually get cycles. You actually get a cyclic situation, and then things become more tricky. Yeah, the portal trees are no longer portal trees if you have holes in the grid graph. And that makes a big difference because in the tree, the path connecting any two nodes is unique. So there are no choices here, right? So once you switch to more complicated abstractions, then you have to do more. Actually, I'm just wondering if you can compute shortest path. No, it doesn't work out. I was just wondering whether if you can compute shortest path in these other abstractions, that adding up the vertical and horizontal distance still gives you shortest path, but I think it doesn't work. Haven't thought it completely through, but I think we discovered at some point that this easy approach doesn't work. It's more complicated.
With the holes? Or?
Yeah, with holes. I think even if you could compute the shortest, if you could compute distances in these more complex graphs, I think you cannot simply add them up. Because there might be one detour where the number of horizontal moves is lower and the other one where the number of vertical moves is lower, and if you add these two up, you come up with a path that doesn't exist. I think that's a short story. Yeah.
But initially you started here with the grid graph that has these holes, and now we're just defining them away, or?
Yeah, it would be nice to define holes away. In fact, Phil and Fabian and so on, they know how much trouble we had to deal with holes. So there are still some regional decompositions one can do in order to come up with a reasonable abstraction of these graphs so that you can still solve the shortest path problem, even if you do have holes, but the runtime scales with the number of holes. Unfortunately, quadratically, I think that's still the best solution, right? If I have k holes, it's like k squared times log n or so, as far as I remember. So that was our initial solution. Yeah, because what you can show is basically with k holes, you can come up with an abstraction of the graph where you can basically cut the graph into k squared subgraphs. Yeah? And once every node has information about these k squared subgraphs, then it can somehow figure out what the way through these subgraphs should be. And then internally, within these subgraphs, they are hole-free, and then you can use the traditional strategy at a high level. That is, in some sense, the approach. Our guess is that you can come up with a better decomposition. Did we come up with a lower bound? I think k squared is still valid, right? Did we come up with O of k?
We don't know.
Yeah, we don't know, right? So my guess is it might also be possible to come up with a decomposition so that you have O of k, so that you can decompose it into O of k subgraphs, but I think we haven't managed so far. Partly also because in the meantime we found an alternative strategy that solves arbitrary planar graphs, even arbitrary minor free graphs of constant size minors. And that's basically what I'm just sketching next. So a general strategy for grid graphs with holes, or general planar graphs even, is you can make use of so-called shortest path separators. What are shortest path separators? Separators, I guess many of you have heard about, right? That in planar graphs there are these small separators that only involve square root of n many nodes. You can always find a cut through a planar graph, yeah, where if you remove square root of n nodes, this graph falls apart into two subgraphs, yeah? Disconnected graphs. You can even have a much more strict property about these separators. You can even assume that they are shortest path separators in the sense that they that the node set that you take away just consists of two shortest paths in the graph. And the way you do it is basically you can just go for some shortest path tree, and there's always a possibility to pick two nodes in the shortest path tree that have a small hop distance to the root, so that if you take out these two shortest paths, these two paths in this shortest path tree, then the whole thing decomposes into two parts. So basically, you can come up with these separators that just consist of two shortest paths. That's the story. And now, how do I compute, at least, here we are also not precise anymore. Here you just get approximate values, so it's not that you solve the true SSSP problem, but just an approximate version. What you simply do is you find, for this node S, the node along the separator that is closest to S, in some sense. You identify that node on the separator that is closest to S, and you also do that for T. Yeah, in some sense, you just look for closest nodes, and then the path from S to T is that you go from S to the closest node on the separator, then along that separator really to the node that is closest to T, and then from that node along this path to T. And the nice thing is that this path gives you 3 approximation, I think, of the shortest path in the system. Just because it's a shortest path separator, then you can basically make use of this triangle inequality to show that you're not going too much of a detour, that you're not doing too much of a detour. Yeah? And that's the way how you can basically hierarchically decompose the network. Yeah? And then for the remaining networks, again, you can find the shortest path separator, and you like recurse on that. Yeah? In fact, you cannot just solve the SSSP problem, you can do much more. You can even come up with compact routing tables. It's actually a strategy that ultimately leads to the situation that you can find for all source destination pairs near shortest paths by setting up compact routing tables, by basically storing information about the breadth first search trees towards the separator from every node. Yeah? And by basically storing the separator, because then for each level you just have to store a logarithmic amount of information, and since every node is only participating in a logarithmic number of levels, it means it has to store too much information. That's in some sense very roughly the idea. The big question is, of course, how do you find shortest path separators in arbitrary planar graphs? That was quite of some headache because coming up with like exact solutions is again a difficult issue, but what you can basically do is you can come up with some sampling tricks that in some sense reveals an approximate version of a shortest path separator eventually, and this is good enough for you to separate the graphs into 2 pieces. But it massively makes use of random sampling techniques, of advanced random sampling techniques, so I won't go into details. And so after all, you can basically, in a polylogarithmic number of communication rounds, you can do this thing so that you not only solve an approximate version of the SSSP problem, you can even get further, as I said, you can come up with compact routing tables that give you for every source destination pair, in some sense that give you information so that you find near shortest paths for every source destination pair. Yeah. How can we deal with general graphs? Since there's not much time left, I just wanted to present a very simple SSSP heuristic to you, and I thought I shouldn't go into more details than that. So here is a very simple, simplistic strategy you can possibly go for. You first compute a minimum spanning tree, T, for node S as a starting point. Of course, a minimum spanning tree might be far away from a shortest path tree, right? But you might just go for this minimum spanning tree, and then you iteratively revise this tree. Yeah, so you use the tree distance algorithm, which to compute the distances with respect to this minimum spanning tree that every node has to the source S, which we know can be done in logarithmic time. And then each node then checks for all nodes in its local neighborhood whether it can improve the situation by switching to a different node as its parent in this tree. It's like a standard trick that is known from sequential shortest path algorithms. In some sense, it's the same criterion that is inherent in this Dijkstra algorithm, for example, if you compute shortest path in Dijkstra's algorithm, or Bellman-Ford, where in some sense you know you're done in a sense that you found the shortest path tree. You find the shortest path tree whenever no node can improve it anymore. So when no node finds a neighbor via which it can go, via which it has a shorter distance to the source. Whenever you reach this point, you know you found the shortest path tree. It's a very simple local criterion. Yeah? And so you can just keep iterating until you're done. And this leads to a shortest path tree. The question is, of course, how quickly, right? But here's just a very simple example where things are not so good. So, for example, you can set up the edge weights in such a way so that the minimum spanning tree is far away from a shortest path tree, like in this particular example. Yeah, so the source node S, as you see, is in the lower left corner. And so the minimum spanning tree is taking a large detour. Yeah. And now all the nodes compute their distances, and after they computed the distances in the minimum spanning tree, they obviously observe that there are shortcuts. Yeah? Because this node at the very end of the minimum spanning tree, for example, observes that it's of course it's much closer to S if it takes S as the parent of its tree, yeah, and not goes via the current parent. Yeah, and the right node of this last node is also observing that, and the node afterwards also. So they're like switching to this new tree that you find at the bottom of the page. Yeah, so they get closer, but not all the way there yet, because still there are nodes that are discovering that they can go for alternative parents, which would get them closer to the source. Yeah, and so you have one more iteration, but then you are done. Yeah, so then you have a shortest path tree. The interesting thing is, I have no clue whether this could work out well in practice. I don't know. There are pathological cases, so you can construct settings like this one, yeah, where it's not only the case that your minimum spanning tree is far away from a shortest path tree, it's also the case that you have to go through theta of n iterations to arrive at the shortest path tree. Yeah. My belief is that this is true for pathological cases, but in practice this might actually run quite well. But I have no clue how to prove it, because as I said, the worst case is really bad. So you would have to do some, I don't know whether smooth analysis is already good enough, like where you perturb the costs of the edges or whatever. I'm not really sure. I like simplistic approaches. Yeah, that's why I present it here, because it's so simple. Yeah, and in practice it should probably easily outrun these more complex approaches that come up with polylogarithmic runtimes because of the extremely low constants involved, yeah, in this approach. So I think for practical purposes, this is probably a reasonable strategy, but as I said, in pathological cases, oh yeah, and here I just proved the correctness. For pathological cases, this might be pretty bad. Okay, I don't want to say anything more about shortest path. Let's switch to rapid reconfigurations. Oh, and that's not the end of the story, so there are some open problems afterwards. So don't worry that I'm running out of slides after that. Rapid reconfigurations. What do I want to achieve here? I want the network established via global edges to rapidly change over time. I don't want it to be stable. I really want to change it so quickly that, you know, in an amount that is as short as possible, I'm dealing with a completely different global network. Why is this interesting? So the goal is actually, the overarching goal is maintaining connectivity in the global network. Of course, if no nodes leave and enter the system in the meantime, that's easy because you know, if the local network is connected, the global is connected for free. So that seems to be a silly question. But if nodes enter and leave, then it might not at all be trivial to maintain a global network. And remember, if we have a wireless ad hoc network, right, where connections break all the time because nodes are getting out of range, and then I cannot establish the connection between two nodes anymore, right, then it might very well happen that the local network gets disconnected, right? And I want to discover such cases via the global network. I at least want to maintain connectivity via the global network so that I can figure out what's going on in the local network. Yeah? And also in the wireless context, of course, in the wireless ad hoc network, nodes might frequently enter and leave the network. And I also want to maintain connectivity in the global network so that I can keep track of what's going on. Yeah? Because if I know, for example, that I run into disconnectivity in the local network, I can now use global edges to re-establish connectivity, yeah? Which is important. Another very important issue, irrespective of hybrid networks, if we consider, for example, peer-to-peer networks over the internet, then rapidly changing the network topology of a peer-to-peer network has also been a way to avoid eclipse attacks by Byzantine peers. Yeah, so eclipse attacks are attacks where, where an adversary tries to isolate a node from the rest of the network. Yeah? And if the peer-to-peer network sits, if it is stable, yeah, if it doesn't change, then it's really like a sitting duck. Yeah? An adversary just has to, you know, use enough time to learn about the topology of the network, and there are ways to learn about the topology, to crawl the network in some sense so that you learn what's going on, who's connected to whom. And once you have that information, you just, when you attack, for example, the neighbors of a peer, then even if a peer is quite powerful and you cannot attack it directly, then by just attacking its neighborhood, you can easily isolate it from the rest of the network, and that's bad. But you can only use these attacks if you know the neighborhood, right? If you don't know the neighborhood, then it's a completely different game. Yeah? So rapidly changing the topology is one possible strategy that you can use to counter such attacks. Because if the adversary doesn't know the topology, it's much harder to isolate nodes. Yeah, and as I said before, the network also becomes much more robust against churn, so frequently joining and leaving nodes. Okay. What kind of graph might be useful here as a base graph for our rapidly changing global network? We'll use here as a base graph an so-called H graph. An H graph is an undirected multigraph consisting of C Hamiltonian cycles, yeah, over all nodes in V. So here you see that this graph consists of two Hamiltonian cycles. Yeah, one here, this green cycle, and the other one is blue. There are just two cycles. And what I want to do is I want to create an H graph consisting of random Hamiltonian cycles. Why would it be interesting to choose these Hamiltonian cycles at random? Does anyone have an idea? What does it give us if they are chosen at random? It's known that even for two cycles, it's an expander graph with high probability. In fact, it's known that even if you have nodes connected to a cycle and you have a random matching in the graph, even that would give you an expander graph already. So that would give an expander graph of degree 3, which is best possible. So here it would be an expander graph of degree 4. Yeah? So just having kind of a random cycle on top of any cycle, right? I mean, one of the cycles can be any cycle. The important thing is just that the other one is random. It's completely random with respect to the cycle that we are establishing. It gives us an expander graph. Is there anyone who doesn't know what an expander graph is? I'm happy to explain that. Okay, good. An expander graph is a graph that has, where every subset of the graph has a large neighborhood. So take a graph, yeah? Take a graph and any subset of the nodes. Oh, okay. Take any subset of the nodes of a size at most half of the nodes. Yeah, so this has at most half of the nodes. Yeah? And now look at the neighborhood, like all the nodes that are neighbors of this node that are outside of that set. Yeah, and so let's call this set U, and the neighborhood is usually called gamma of U. And whenever we can ensure that gamma of U is at least some constant alpha times the size of U. Right? For any subset U of at most half of the nodes. Of course, I mean, if I go beyond that, then eventually there's no way that I can have such a large neighborhood. But if up to that size, we still have a neighborhood that is really large in the sense that alpha must be a constant larger than 0, of course, right? The best value for alpha, by the way, is 1, of course, right? Because at best, the neighborhood can cover all other nodes, yeah? And so the expansion can be 1 in the best case. In the worst case, it's 0. So therefore, it's always, alpha is always a value between 0 and 1. And the closer it is to 1, the better. Yeah?
And so does this have to hold for all U of...
Yeah, for all subsets U.
And most have, or only for those exactly?
Yes, for all subsets U. We have to have this property.
So we can start small and grow.
Yeah. Yeah. And so it's no wonder that the diameter of an expander graph must always be logarithmic. So it's at most O of log n. Yeah, in the best case, if you have a clique, I mean, a clique obviously is also an expander graph. Yeah, it trivially satisfies this property with alpha equals 1. So the clique is the best possible expander graph that you can potentially have, of course, because it includes all edges, right? Then definitely it satisfies this property. What people have been looking for then in the past was what is the lowest possible degree that you can use so that you still have an expander graph? Yeah, and first there were just some random constructions that people came up with, like this random H graph. Yeah, and they had a hard time coming up with explicit expander constructions because it's actually very complicated because expander graphs by nature must be quite irregular. Yeah, because regular graphs, they tend to have the property that the expansion is not so good. In fact, people, of course, have looked at all these standard graphs like butterfly networks, De Bruijn graphs, hypercubes, for example. In case you know that, these graphs are pretty good. Hypercubes, for example, like they're graphs in some sense that they look similar to high-dimensional hypercubes, yeah, that's why they're called hypercubes. They have a logarithmic degree, they even have an expansion of 1 over square root of log n, so it's pretty good, but it's not going all the way to a constant. But then people came up with explicit constructions even, where graphs of constant degree were constructed that give you constant expansion, which was quite amazing, right, that this worked. Some of the best graphs are so-called Ramanujan graphs. Maybe you have heard about them. Called after some famous Indian mathematician that had some hypothesis, and it turned out that that was true, and the base of that hypothesis was the base of the construction of that graph, and it doesn't just give you a high expansion, it even gives you a high girth in the sense that every cycle in the graph must be of large size, of logarithmic size even. So it basically gives you almost the best possible expansion you can even hope for. Because locally, the neighborhood of a node even looks like a tree. Yeah? So they can be constructed. Highly complex to prove that graphs are expander graphs. The easiest way to construct an expander graph is actually by making random decisions like this one. And for those of you that have heard about skip graphs, to my mind, skip graphs are my favorite expander graphs because skip graphs are extremely easy to construct and also locally maintain. That also give you this nice expansion result. Expander graphs are very important because due to their high neighborhood size, they're extremely resilient against disconnections. Yeah? Because a large number of nodes must die just to have any chance of disconnecting a large number of nodes from the rest of the network. Because like for that subset, like if the subset U is reasonably large, then you really have to kill a lot of nodes in a very specific neighborhood also, right? That you have to know in some sense. Like even worst case situations can be handled quite well in expander graphs. So expander graphs are to my mind, the best graphs you can hope for overlay networks, for example, in the internet, because they give you the highest resilience. Yeah? So therefore, expander graphs are definitely a good approach. But of course, even if you do have an expander graph and you let the adversary explore this expander graph, then everything is in vain, right? Because this expander graph just has a degree of 4, so if the adversary has enough time to explore it, it can still the neighborhood of every node, and it can easily perform eclipse attacks. So that alone does not help. It helps against so-called oblivious adversaries, so adversaries that do not know the structure, because then even if it can attack a large fraction of the nodes, chances are very low that it can even isolate a single node. Yeah? At least if the degree of every node is sufficiently large. Actually, do you know what kind of degree you need so that you can even be resilient against a constant fraction of attacks on nodes, like DOS attacks, where you then remove them from the network? Which degree would be sufficient so that you wouldn't even lose a single node of the remaining nodes? Any guess? Actually, a logarithmic degree works out, because if you are connected to a logarithmic number of other nodes, and every one of these nodes has a constant probability of dying, then the probability of all of them dying is polynomially small in n. Yeah, because it's a constant probability to the power of the neighborhood size. Yeah, and if the neighborhood size is a sufficiently large constant times log n, then chances are very low that you will be isolated. Yeah? So in some sense, this random H graph with just 2 cycles is still a bit too vulnerable to massive denial of service attacks, like to massive attacks that shut down lots of nodes. But an easy generalization to just log n random cycles would do the job. Yeah? And then you really have an extremely resilient network. Okay, but here for simplicity, we just assume that the number of cycles is a constant. Oh, and by the way, if I say with high probability, because not everybody in every community has this, maybe the same understanding of that, with high probability, or short form is WHP, means that with the probability of at least 1 minus 1 over n to some constant that is sufficiently large, that you can basically set as large as you like, depending on the parameters that you use for the construction. Yeah, so basically, if you say something happens with high probability, you mean that the opposite event is extremely unlikely to happen, extremely unlikely. So basically, it forms an expander with high probability. So it's extremely unlikely that there will be a single subset U that has a bad property. Although, wait. Well, I think you have to have sufficiently large subsets. I have to think about it, whether you need a lower bound of log n or something before it really holds. One has to be a bit careful probably about that one. Oh, no, should be fine. No, should be fine. Okay, and this is the paper detailing this. Okay. Yeah, and here this is just summarizing a random H graph consisting of at least 2 cycles, has a degree of 2c and a diameter of log n with high probability, because once you have a high expansion, it's basically very easy to show, because whenever your neighborhood is of constant size of your current node set U, you see that the number of nodes that you reach in each round is always going up, or the set of nodes is always going up by a 1 plus alpha factor, right? Because you start with 1 node, you have at least alpha nodes in the first round, so altogether, like alpha new nodes, so altogether you have 1 plus alpha nodes, and then you apply the expansion again, giving you 1 plus alpha squared nodes, at least that you reach within 2 hops. Within I hops in general, you can reach at least 1 plus alpha to the power of I many nodes. So definitely after a logarithmic number of rounds, you will reach at least half of the nodes. And then via some easy proof that also then the number of nodes that haven't been reached yet, then from that point on shrinks by a factor of 2, you can show that the diameter is definitely log n. Yeah, so that is a relatively simple exercise. Yeah. How do we construct a random cycle? So here's the problem that we want to consider. Given a hybrid graph, H equals VLE, where VL is connected and E is initially empty, construct a random cycle C. Yeah, you basically start from scratch again. Of course, what you can do is you can first come up with a well-formed tree, yeah, which we know how to do in O of log n squared rounds, and construct out of T an oriented base cycle. Yeah, every node knows its predecessor and successor in the cycle. I already showed you also how to do that. You just use an Euler tour. You just connect the nodes who appear like the first time in this Euler tour to each other. You basically get a Hamiltonian cycle, which gives you the space cycle. Of course, up to that point, it's not random, right? It's just a cycle. It's not picked uniformly at random among all possible cycles. It's just a base cycle that you get. So then what you do is you can, like one strategy is you can set up shortcuts on top of B, yeah? And use them to set up hypercubic connections. And I will tell you soon what I mean with this, right? And then you use the hypercubic connections to generate a random cycle, or like an almost random cycle. I should say. Okay. Like way back, I mentioned already how to transform, in some sense I mentioned techniques how to transform a well-formed tree into an oriented cycle, yeah? So you can use virtual nodes, and you can connect the first appearance of these virtual nodes to each other so that you get this, this base cycle. But at that point, you know, it might not be random. Then what you do is you again establish these shortcuts, yeah? Via this pointer doubling strategy that I explained before, on top of that base cycle. Yeah, and that terminates in, you know, eventually when you cannot construct any further shortcuts. So now, in order to establish hypercubic connections, you just throw away some of these shortcuts. Basically, what you do is you first compute all the nodes to the starting node of that line. Yeah, so you assume that one node is in some sense the root node, or has already been selected as root node, so that you can basically cut this Euler tour into a line. And of course, the list distance problem, we already know how to compute it in logarithmic time. And now what the nodes simply do is, after they know their hop distance from the root, is they interpret this as a binary label. And they keep an edge with a neighbor whenever the binary label of the neighbor has a Hamming distance of 1 to the own binary label. Hamming distance 1 means that the bit sequence representing this binary label really differs only in exactly 1 bit. Yeah, so you can go from one node to the other just by performing 1 bit flip. Yeah, so just again, so you interpret these as binary labels where the root node has label 0, right? Like this has value 0, next one has label, binary label corresponding to 1, then corresponding to 2, corresponding to 3. So you establish binary labels. You compare the binary labels with your neighbors, and whenever the Hamming distance between the binary labels is just 1, you keep that edge. And that gives you the so-called hypercubic edges. Why? Because these are exactly the edges that the hypercube would consist of. Yeah? In fact, well, it's not, like if the number of nodes is a power of 2, it's actually exactly in a hypercube. Otherwise, it's just an approximation of a hypercube, I should say, because there are some additional edges. And now what you do is, you now just do some very simple flipping. It's like similar to card shuffling, maybe, if you wish, right? So k many times for some constant k at least 3, you do the following. You go through all these edges from the lowest level shortcuts to the highest level shortcuts, and you decide with probability 1/2 whether you should flip the 2 nodes in this line. That's all you do. You decide with probability 1/2 whether to flip the nodes. And at the beginning, you just use these blue edges here. So just the nodes connected via the blue edges now make a random decision with probability 1/2 whether they should switch their order. And what can happen is that, for example, the nodes 3 and 2, you know, see that? In this picture, nodes 3 and 2, for example, decide to switch their order on this cycle, yeah, with probability 1/2, but other nodes, for example, 6 and 7, they decide they keep their order as it is. Yeah, it's very simple. And then the green edges are used, like the next higher level is used for the flipping. Again, some random flipping. Yeah, so like the root and the node 3 decide to flip, but 1 and 2 do not decide to flip, so they keep their order. So they just decide to flip. And again, then the next higher level decisions are made. For example, 7 and 1, for the next higher level shortcuts decide to flip, and 5 and 3 also decide to flip, but 6 and R, for example, not decide to flip. Very simple. And just a constant number of times, you just go through all the shortcuts, and for each shortcut, one after the other, you make this random decision. And it turns out that the outcome is an almost random cycle. Yeah, if you do that in some sense often enough. Like it perturbs things sufficiently well after applying this a constant number of times so that your outcome is random. Maybe just to give you an intuition about that, why hypercubic edges are so convenient. It turns out if you just do this for 2 iterations, you can already realize any permutation. Yeah, if you just take these hypercubic edges and you just apply them twice. Yeah, you go twice through all the edges. There is a strategy of doing flippings according to this strategy here, so that you can arrange the nodes in an arbitrary permutation. Yeah, just going through it twice is already sufficient to reach an arbitrary permutation of nodes on the cycle, but it doesn't give you a random permutation because some permutations are more likely than others. So in some sense, to get sufficiently close to randomness, you have to repeat this a constant number of times. That is the intuition. Okay. So therefore, if you sum it up, so we start with an arbitrary local network. Very quickly, you can establish a well-formed tree. Out of the well-formed tree, you can create a base cycle, which is this green cycle, right? And then the other blue cycle is just constructed randomly on top of that via these hypercubic flippings, so that in O of log n squared time, you can construct a random H graph starting with an arbitrary graph. But log n squared is a lot of time. In practice, log n squared is a large number. You want to be faster than that, yeah? So the question is, can we accelerate the construction of a new random H graph once we have already set up a random H graph? So let's say we can start already with the H graph. So maybe like, okay, it takes a while. In effect, in the worst case, it might even, even in the best case, even in the best case, the lower bound is log n, because we might initially have a local network of diameter n. Yeah? So just to construct the first H graph would already need a local n number of rounds. But then hopefully from that point on, it is quicker to achieve. By the way, you remind me again concerning the time. Okay. Yeah. So can I do it more quickly? Recall the random cycle construction. What we do is C many times for some constant C, at least 3. We go through all the levels of the shortcuts and we make these random decisions of doing the flipping. Yeah? The question is, can we speed that up? Can we find out about the final result, right? The end result of this flipping? Can we find out about the final result faster than in a logarithmic number of rounds? Which sounds odd, because in some sense you have to go through it step by step, and how can you possibly get faster than just exploiting the full parallelism of that algorithm? Of course, you have to think a step further, and then you see that you can accelerate that. The idea to accelerate that is the following. So initially, all nodes, they internally already make a decision which of their edges to switch over all iterations of the algorithm, right? I mean, they can throw coins already for all of the shortcuts at once, in one step, and then just follow the random choices from that point on. So basically, after the nodes did their random choices in the first round, from that point on, the end result is already predetermined. The problem is only that each node doesn't know its final position yet. But once the random choices have all been done initially, from that point on, it's just a deterministic algorithm. Yeah? Because from that point on, the nodes would just follow their random choices done initially in this algorithm, and they are done. So how can we accelerate this deterministic flipping then? We can do it because after the random choices have been done, the path that a node takes, so in some sense, if we follow over the time the different positions that the node takes in this hypercubic network, in this time graph, if you roll it out over time, what you basically have is a path, along the cycle edges, along the shortcut edges of that base cycle, It's a path that basically tells us which node positions a node is going through in order to find its final position. And this path has a length of log n, and why not also do pointer doubling on top of that path? so that we find the final position in log n many communication rounds. Because these paths are disjoint. Because for this algorithm, at any point in time, every node will, of course, occupy one unique position. There won't be any overlap of the nodes, right? So every node will occupy a unique position at any time point. So these paths, if you roll this out, and I will soon show a picture, it's disjoint. So basically, this is kind of a rollout. So this is like two iterations, the second iteration has just started of what the nodes can do. So remember, at the first step, the node can just switch positions with their direct neighbors, because these shortcuts at level 0, they just connect nodes to their direct neighbors. So basically, it gives you this kind of very simple switching result. Then remember, in the next iteration, where you use shortcuts at level 1, each node would, in fact, switch positions with neighbors of distance 2. So the outcome, the set of all possible outcomes is then represented by this switching network that you see here. And then nodes would switch positions at nodes of distance 4. So the outcome is then at the next layer, displayed at the next layer. For those of you that have heard about this network, that's also called a butterfly network. It's kind of a, if you roll out some decisions you make over edges of the hypercube for increasing dimensions, then you can also display it as a so-called butterfly network. Anyway, if you haven't heard about this, doesn't matter. But the thing what I want to say is you can now basically represent the decisions that you take over time. You can represent it as a graph. Yeah? And now what the node now does here, the root node, is it follows a certain path of decisions where, for example, when the level 0 shortcuts are considered, here this red edge means that it switches its position with node 1, because the random decision has been made initially that there should be some switching here. In the next level, when R has this position that previously was held by 1, the decision was not to flip. So therefore, R just stays at its current position. Then at level 2 shortcuts, again, R would decide to flip its position with the neighbor. And so, it would end up at the position of node 5. Yeah, and then again, there would be some flipping. So it would then switch to position 4. And then its final position here, at least as far as I displayed it here, the switching decisions is then at position 4. In some sense, it's really just a path. And as I said, these paths are disjoint because at any point in time, every node will just occupy a unique position. Yeah? It's not possible that two nodes can occupy the same positions because I always use this switching, right? So they just switch positions, which means that it can never happen that two nodes arrive at the same position. Okay, so we have a collection of disjoint paths. And for these disjoint paths, we can now just play the pointer doubling strategy to make them shorter. Because what I just have to figure out here for the root node is the position that it ends up with. So here I just displayed it to position 4. So for example, the root node wants to learn that after 5 iterations, it ends up at position 4. Okay, yeah, I already mentioned that they are no disjoint. So we know that they are having fixed paths, these nodes. And each node can, of course, determine the predecessor and successor position of any path passing it also. Yeah, because whichever node ends up at this node, it can contact one of its shortcut neighbors in order to figure out whether there would have been a decision to do some switching or not. And also for the next step, it can figure out whether there would be another switching decision at that place or not. So each node can locally figure out what is the predecessor and successor of a path passing it at a certain stage of that switching strategy. Yeah? And because they can figure that out, what's the predecessor and successor of every path, these can now be stitched together, these paths. because now it can introduce the predecessor and successor to each other to produce a shortcut on top of that path. Yeah? Here maybe I just go for the picture here. Oh, and by the way, each column in this time network is always emulated by a single node. Yeah? So node 3 is responsible for all the paths that are passing through that column. Yeah? And that, for example, allows us to say that, for example, for node 1, it can figure out that whoever ends up at the position of this node 1 after 2 switchings, for example, it can figure out just by looking at its own random decisions that the previous decision was 1 as well, because there was no switching here, but the next time there was some switching. So it can figure out the predecessor and the successor of the red path without knowing who's the ultimate starting point of the red path and who's the ultimate end point of the red path. But a node doesn't have to know it. It just has to know which path is passing it at which point. And that really just depends on the random bits that have already been selected. Yeah? That's all a node has to do. And once it knows the predecessor and successor for the path passing it at a certain stage, it can do this predecessor-successor introduction. And because the depth of the whole thing is just O of log n, it just needs to do some O of log n introductions, which it can easily do because we allow a polylogarithmic number of information, of bits to be exchanged, yeah, in each round by each node. Yeah, so it can basically do these predecessor-successor introductions all at once in parallel. Yeah, for all the paths that pass through it at every stage. So that massively in parallel, for each of these paths, shortcuts are established, right? So now we have edges basically bridging a distance of 2 in each of these paths. And we continue from there, because once a node knows its distance to predecessor and its distance to successor, then it can introduce these two so that we already form shortcuts of length 4. Yeah? So it continues like that. So basically here, then, a shortcut of distance 4 is already established because this node here at level 2 at position 1 can introduce the distance 2 predecessor with the distance 2 successor to establish a distance 4 shortcut or level 2 shortcut. Okay, and this is continued until no further shortcuts are possible, and of course log n many iterations are sufficient for that. Yeah. So a node can determine its final position within log n many hops. Yeah, that's the outcome. And then after having located this final position, the node just moves to that position, right? At the nodes there, then the original nodes will be informed about which node will end up being at this position, and the initial nodes then do the introductions between the new nodes so that the new nodes form a cycle as well. Okay, that's it. Yeah, so using the accelerated cycle construction, we get that if we are already given a cycle with hypercubic shortcuts, a near-random H-graph can be constructed in time O of log n. But we are not yet there, right? Because we wanted to get from an H-graph to an H-graph. And here we assume that we already have these hypercubic shortcuts, yeah, on top of the base cycle. But in order to set up the hypercubic shortcuts, I need logarithmic time because the base cycle has a length of n, yeah, or a diameter of n. So just establishing the hypercubic shortcuts would take me a logarithmic amount of time. So that's bad. So it doesn't give me any advantage at the end, yeah, if I want to go from an H-graph to an H-graph. So I have to do something else. Any idea what else I can do? Because I really want to end up with a construction where I can get from any H-graph to any other H-graph, where the follow-up H-graph is like completely independent of the previous one, yeah, ideally. In just O of log n rounds, without any further assumptions. Any ideas what we can do? Of course, the strategy is completely different. We drop this hypercubic connection stuff because it doesn't get us anywhere. It was a nice trick to see that paths can be made shorter and shorter. but establishing the shortcuts is the dead end somehow. Yeah. So what we instead do is we remember ourselves that an H-graph is an expander graph. And what can you do particularly well in expander graphs? Random walks. Yeah? Because it's known in an expander graph that if you just do a random walk for O of log n hops, you end up at a node in an expander graph almost uniformly at random. Yeah, if you have a regular expander graph, so all the nodes have the same degree, of course, we have to assume that. If you just perform O of log n hops, like randomly, through the expander graph, you just end up at a node chosen almost uniformly at random. That's good enough. Yeah? Okay, so we are switching to a random walk approach. So what the nodes are doing, because ultimately we want to set up C random cycles, let's say, what we then simply do is we perform C random walks in parallel of length O of log n for each node. Like each node, right, in parallel, like every node in the H graph starts C many random walks of length O of log n. And then wherever the walks start, you know, the nodes consider this node as their endpoint. Of course, there's still a problem with this because with random walks, you cannot guarantee anymore that every node will be the destination of exactly one of these random walks or exactly C of these random walks so that you can nicely construct these cycles. It's a bit more complicated, yeah? But let's see where we end up when we are using this approach. Yeah, so we want then, for the destinations of these random walks, we want to make use of them to construct new cycles. Okay, so for the moment, let's ignore how to do the random walks fast. Let's just assume that we know the destinations of the random walks. Yeah, let's say the nodes want to establish a new random-looking blue cycle, and let's say the random walks that were done for this blue cycle ended up as distributed in this picture. Like the random walks of nodes 4, 2, and 6 happen to end up at node 2. Yeah? What can be shown is, first of all, that not more than a logarithmic number of random walks will end up in one node with high probability. So there won't be too much congestion, simply because of the fact that it's known that random walks end up at nodes distributed uniformly at random or almost uniformly at random when they're performing O of log n hops. Yeah?
Can't you reduce it to constant by making the walks dependent on each other?
Yeah, you can, but as we will see, it's not needed really. Even with that, you can easily construct a cycle out of that, yeah. Yeah. So here you don't have to spend too much effort, right? You just let them run, yeah.
I mean, you just have to make sure that you always send the walks you have on different edges. That's all you need to make sure.
Yeah, and I will later explain how to do these random walks. That's also another complication. But for now, so one thing that can be shown is that not too many. Actually, if you do a more precise analysis, you can also show that at most log n over log n many endpoints of random walks are at the same node, but let's forget about these little details. That's the one thing that I can show. The other thing I can show is that there are at most a logarithmic number of consecutive nodes that will not be the endpoint of a random walk. So the distance between two nodes along this cycle, this base cycle as I call it, the distance between two nodes that are the endpoint of at least one random walk is at most log n with high probability. Yeah. So now how can I, out of these like not really nicely distributed random walks, how can I construct a base cycle? Well, one thing is easy because if multiple random walks end up at a single node, because there are not too many, these nodes just chooses some canonical ordering. Some canonical ordering maybe by the random bits of the, whatever, right? Something where the outcome is random. Yeah. Or I could also just go for a random, random ordering, whatever. I think random ordering is the simplest. So it just randomly orders these nodes internally and just informs 4, for example, that 2 is its successor and and 2, for example, that 4 is its predecessor and 6 is its successor, right? So this can be done locally. Then whenever two nodes are adjacent to each other that are the endpoints of random walks, is also very easy, right? Because whoever is the first node in this ordering with respect to node 2, it just tells its predecessor, hey, my first node that I'm starting with for the cycle is 4th, so what is your last node? And that node here says, okay, with label 1 says, oh, it's 5. So then 4 and 5 are introduced to each other. So that's also easy. The only thing is if there's a sequence of nodes that is not the endpoint of any random walk, because still 6, for example, has to know its successor, which would be 8 in this case. Yeah? But again, if the distance between the node holding 6 and 8, if the distance is at most log n, I can make, again, use of pointer doubling, so that 6 learns about its successor in log n many rounds. Yeah? So that's completely uncritical. So therefore, you know, just coming up with a cycle out of these endpoints of the random walks, that can be done in log n rounds. How can I emulate these random walks in O of log n rounds as well? Because I don't want to spend O of log n rounds for the random walks. I want to do it in log n rounds. So here's the idea that I do. Each node starts with 2 bags, where the first index here, this 0, represents basically a bag at level 0, where it selects at random out of its neighbors incoming edges. These are stored in this bag 0, in, and outgoing edges which are stored in this bag 0, out. And it generates for each bag some constant time c plus log n, where remember c is the number of cycles that I want to create. Some c plus log n times log n many incoming and outgoing edges. 5 minutes for each of these bags. Yeah. And these are just pieces of random walks, right? So basically, these bags just tell this node v, well, there are theta of c plus log n times log n many random walks that enter me, and there are c plus log n times log n many random walks that are leaving me. But now the node v needs to stitch these random walk pieces together. So what it does is it just randomly pairs off these edges in B0 in and B out. Yeah, it basically stitches them together, and now it makes a decision whether, if it stitches them together, of course, it gives us a random walk piece of length 2, right? Because an incoming walk is connected, like an incoming edge is connected to an outgoing edge. So now we have like a random walk piece of length 2. And now it needs to decide whether this random walk piece of length 2 is either stored in the incoming buffer of W or the outgoing buffer of U. So it has to make a decision. It's either stored in W or in U. Yeah? So if it decides that it stores it in U, then U will basically remember it as a walk of length 2 that ends up at W. Yeah? A walk that leaves the node U that ends up in W after 2 hops. That's what U is remembering. Or if V decides to store it in W, then W remembers it as a walk of length 2 that starts at node U. Yeah? So the intermediate nodes, the nodes can forget about. They don't have to record these. Every node just has to remember for its incoming bag what is the original destination of that random walk. Yeah? And for its outgoing bag, what is the final endpoint of that random walk that is sourced there. Yeah, so basically in one iteration, it can already stitch together random walk pieces of length 1, 2 random walk pieces of length 2. Yeah? And this decision whether to store it in U and W is done with probability 1/2. Yeah? One of these 2 nodes gets the piece with probability 1/2. We have to do it, we only can give it to one of them because otherwise, if we give it to both of them, then there will be inconsistent stitchings and things go wrong. So we just want one of these nodes to follow up with this piece. And if you start with sufficiently many random walk pieces, you can continue stitching these random walks together to longer and longer random walks for log n plus d many stages, basically. Yeah? And this gives then random walks of length d times log n, actually, which is good enough for us. And it really works in a way that in bi, in, each node v would store random walks of length I, and of length 2 to the power of I. And in bi, out, each node v would store random walks also of length 2 to the power of I that start at v and end at some node. And it will again stitch these pairs them off at random to establish random walks of length 2 to the power of I plus 1, which will either be introduced to u as an outgoing random walk or to w as an incoming random walk. Okay. They continue doing it. At the end, there are sufficiently many random walks left. At the end, there are basically theta of c plus log n random walks left with high probability. Yeah? So basically, each node v ends up with theta of c plus log n many edges in bk out after k equals log n plus d iterations, which is good enough so that in some sense we have c plus log n many random walks of length d times log n. And we just make use of these to establish our endpoints. Yeah? These are the random walks that are starting with node v. Yeah, and then just, yeah, as I said, v picks just c of them. And then we'll go from there. And we already saw how to basically stitch the endpoints of random walks together so that, yeah, if every node can send and receive log n squared messages in each round, which is okay because for the global edges we allow a polylogarithmic of communication, amount of communication, we can basically go from a random H graph to a new random H graph in O of log n communication mounts. Yeah, one motivation, as I already mentioned, is that, oh, I should finish, right? I will wrap it up now. So recall the original motivation that this H graph is very robust against churn because it's an expander. But it's also very good for joining a peer-to-peer system or leaving, because imagine that a new node wants to join. It's extremely simple because what the new node simply does is the node contacted by the new node, because the new node needs to contact one of these nodes. Yeah? To integrate a new node, it's extremely simple because it just has to integrate it into all of its cycles. Yeah, it just has to integrate it as its successor, for example, in each of its cycles, and it can just introduce this new node to its predecessor, which is itself, and the successor, which is its old successor. Yeah, so integrating a new node can be done in a constant number of rounds with an H graph. So it's extremely efficient. Of course, it loses its expansion property if a node would introduce too many nodes. So if every node just integrates a constant number of nodes, you know, in log n many rounds, then it's good enough. Yeah, leaving a node graph is equally easy in H graph because a leaving node just has to introduce its predecessor and successor to each other, so that if we allow them to leave nicely, then this can also be handled in one round, basically. That's a big advantage, right? And you always get back to a correct structure. Yeah? You might lose expansion properties, but the structure can always be maintained. That's a nice thing. Another nice thing at the very end is you can very efficiently simulate the so-called gossip model. In the gossip model, every node can only execute push and pull operations in each round, and in a push operation, it can send a message to a random node, while in a pull operation, it can ask a random node to send it a message. And simulating that can be done in constant time by this rapidly changing network approach, because it gives you enough randomness. It gives you like random connections every log n many rounds, and if you are asking for log n many random connections every log n rounds, it gives you enough randomness so that you can faithfully emulate any algorithm that was originally designed for the gossip model, where the only communication you allow is that it interacts with a random node, chosen uniformly at random. Yeah? And very efficient algorithms are known for the gossip model, so you can basically emulate it in, with global edges with constant slowdown, which is particularly nice. Okay, let's stop here and have another break then. Just continue and no announcements? Okay. Oh, say, okay. So, yeah, let's continue. First of all, the gossip model that was like dealt with very quickly at the very end, so let me just repeat it once again. So in the gossip model, you assume that you have no knowledge about the underlying network. All that you have is some simple primitive that allows you to contact a random node. However that works, right? This is like, that's a black box, right? You somehow execute a push command, it will go to some random node, yeah? You execute some pull command, you will contact some random node to give you certain information, yeah? You ask a random node to give you some information, no clue who you will be contacting, yeah? But nevertheless, even though it's fairly elementary, you can do some pretty nice stuff with it. You can do lots of things like consensus. You can solve it very efficiently. I can just mention on the side, for example, there's a very simple consensus algorithm where every node contacts two other nodes uniformly at random, yeah, which can be done with two pull operations, and asks them for their current key value, right? So initially every node has a key, you know, it can be arbitrary keys, and every node contacts two other nodes uniformly at random to get their keys, and I assume also that there's a total ordering on the keys. And then what the node simply does is with its own key and the two other keys, it computes the median key and keeps it. Yeah, that's all. The nice thing is that this so-called median rule converges very quickly to a consensus. Namely, you just need a logarithmic number of rounds to converge to a consensus. Yeah, it's extremely fast with high probability. And that thing even works if you have up to square root of n many adversarial nodes. Yeah, that basically try to prevent convergence as much as this is possible. The nodes don't care, they still arrive at a value within, or basically for the up to square root of n nodes, the best bound we have is log n times log n, I should say. It's not perfect, it's not log n, but it's very close to it, what we have. And this can all be done with this gossip model, yeah, with this very primitive model that you quickly arrive at the consensus at a very low work overhead. Yeah, so there are various solutions for the gossip model where you can solve problems very efficiently. Therefore, this is kind of a nice problem, nice model. And if we can emulate this model very effectively, like here, even with constant slowdown, then it means that any algorithm presented there can immediately be taken over to our hybrid network in some sense. Well, actually here also the local network wouldn't even be needed, right? We just rely on the global network. Okay, I promised you in the announcement that I would also say some words about open problems. And let me start with some warm-up problem, yeah, and then we'll go from there. Let's see how far we get. And if we happen to be too quickly through these things, there's some other topic I think that would be very nice as an add-on that I have. I thought that like close to 200 slides would be enough for 3 times 1.5 hours, but it seems that I might even go through them all, which is quite surprising. I hope I wasn't too fast. Let's talk about bipartiteness. So here, given a hybrid graph H equals VLE, where V, L is connected and E is empty, check whether V, L is bipartite. Yeah, I guess you all know what a bipartite graph is, right? I mean, it's elementary graph theory. You can basically partition the node set into 2 sets so that edges only go from one set to the other. Yeah, then the graph is bipartite. I claim that this can be done very quickly, yeah, using the hybrid network approach. Any idea what to do if you want to check bipartiteness? So I try to get you involved now more and more.
Does it help to try coloring it with colors?
Probably most of you know that a graph is bipartite if and only if it's 2 colorable, right? How can you easily check whether a graph is 2 colorable or not? What is the standard approach? Maybe you learned that also in one of your lectures. Maybe it's a long time ago, so you don't maybe remember.
Something like DFS?
Exactly. In fact, any spanning tree is good enough, right? You just find any spanning tree. You color the nodes, right? You assume you have a rooted spanning tree, right? So the root gets color 1, its neighbors get color 2, the next neighbors get color 1 again, and so on. You switch, right? You just color the nodes in your spanning tree, and now you check whether there's any color conflict among the neighbors, in the sense that there's an edge where 2 of the nodes have the same color. You don't even need a BFS tree. Any spanning tree would do. Yeah. If you can, you know, after this, in some sense, this deterministic outcome of the 2 coloring of the spanning tree, if you then see that this is not violating the 2 coloring property between any set of neighbors, you're done. You know it's 2 colorable and you know it's bipartite. But if you find a violation, you know that there must exist an odd length cycle in the graph, and when there exists an odd length cycle, you know it's not 2 colorable. Yeah, it's a well-known result from graph theory, and we already know how to establish a spanning tree, right? It doesn't have to be a shortest path tree. Spanning tree, we know it's like a byproduct of the well-formed tree algorithm. So we use our well-formed tree algorithm to construct a local spanning tree on top of the local edges. Use our rooted tree solution to turn T into a tree rooted at the node with maximum ID. Yeah, of course, this can also be done quite easily. And transform T into a constant degree sibling tree, T prime. Because I just want to come up with a 2 coloring result, and how can I quickly determine the 2 coloring? Well, every node that has an even distance from the root gets color 1. All nodes of odd distance get color 2, right? I mean, so basically you can reduce it to the distance, to the hop distance situation. So that's exactly what you do. So after the transformation into a sibling tree, where the sibling connections are just getting value 0, I mean value 0, then the distance in the sibling tree is then the hop distance in the original tree. And you just do the tree distance computation that we did before, and problem is solved. Yeah, I think I can skip these slides because, yeah, what you can do is, again, I can use this shortcut approach to compute distances, and then I take the distances modulo 2 in this case, and that's the color that the nodes get. And then I just have to do this neighbor check. Right, so every node checks whether there is an edge VW in L with BV equals WW. If so, then V sets X of V to 1, otherwise it sets it to 0. If we want all nodes to know whether it worked out or not, we just aggregate these values upwards, the tree to the root, so that the root knows whether there's at least one node that got a 1. 1 means violation. Yeah. And then the root can also, if it wants to, inform all the nodes via broadcast and log in time whether there was a violation somewhere or not, so that everybody knows about it. That's about it. Okay. So that's easy. So therefore, the bipartiteness problem can be solved in O of log n squared rounds. Max flow. Given a hybrid graph H equals VLE, where VL is connected and E is initially empty, you have some local edge capacity C and the source target pair ST, compute a max flow in VL from S to T. I must admit I haven't really done a thorough literature search, so if someone knows more than me, feel free to speak up. But special cases are really easy, because if the local network is a tree, I mean, what do you need to do if it's a tree for the max flow problem? How much flow you can get from S to T?
You already have one path.
Exactly. And so what do you just need to compute for that path?
The minimum capacity.
Yeah, the minimum edge capacity, right? I mean, it's okay. That's really easy. If the local network is a whole free grid graph, it's a bit more tricky. Does anyone have an idea there? How you can compute a max flow efficiently between any source target pair if it's a grid graph, a whole free grid graph at least. I say it's doable. I must admit, I haven't really thought it through. But I'm pretty sure that determining the bottleneck in a whole free grid graph with respect to two nodes S and T shouldn't be too difficult.
Is it a similar idea with the portals, but instead of keeping the shortest distance, you keep the minimum capacity or something?
Yes, so consider the fact that you determined a shortest path, right, from S to T, which is doable, definitely, via these two portal graphs, right? You don't know just the distance, you also know all the, you can also, from the distance information, can figure out along which path to go, right? In fact, all the nodes can determine that because you see which node gets you further away and which node gets you closer in some sense, right? So in some sense, you can recover the path from the distance information between S and T. And of course, remember that the whole free grid graph, in some sense, the path gives you the unique passage that you have to go through, right? Through the grid graph to get from S to T. So now you only have to figure out how wide is that passage. Yeah? And of course, how can you check how wide this passage is? It has to, yeah?
I would compute the capacity on vertical portals, horizontal portals, and take the minimum, yes.
Yeah. Basically, how many connections can you have between adjacent portals that are relevant for your shortest path? Because you know, after you did the computation for the vertical portal graph, for example, you definitely know along which vertical portals the path has to go. You definitely know that, through which vertical portals your path needs to go. So you can check, in some sense, how well connected adjacent portals are between these vertical portals. It's not the whole story, because you have to go for one more distance, right? Because when you go from portal 1 to 2 and from 2 to 3, then even if portal 1 and 2 are well connected and 2 and 3 are also well connected, that can happen at completely different areas, right? So that portal 2 would still be the bottleneck. So you have to basically go for a distance of 2 to check how much flow you can get through with respect to a distance of 2. But that should tell you how much flow vertical-wise you should be able to ship from the starting node to the end node. Yeah. And my guess is that if you do it for the horizontal and vertical portal graphs, you can probably take the minimum of these two things to either get the exact value or at least some good approximation. As I said, I haven't thought it through, but I think it's doable. If one has a closer look at it, it might be possible to do so. The general case. I don't know, does anyone here already have a solution for the general case? Max flows, we have never looked at it so far.
I don't think it's easy, but I think the undirected graphs, and if you find it a 1 plus epsilon approximate solution, there at least we once developed the congest algorithm, which was basically built on this minor aggregate framework. I mean, back then we didn't call it that way, but probably it can fit that framework, and there we know we can find polylog hybrid algorithms.
So with a hybrid network, you can speed it up to polylogarithmic runtime.
I would assume so.
Okay.
But, maybe, actually with the algorithm we did, it wouldn't be polylog, it would be n to the little of 1. It would be something like exponential.
Okay, so it's...
Some root of log n. But there's much more work on, I mean, there's a lot of recent work on solving max flow
Yes, I mean, max flow, there's a lot happening.
Right, there's a lot that happened
Yeah.
for sequential algorithms.
Yeah. You might have heard about this near linear runtime algorithm for the max flow problem, which was a true breakthrough. Is it submitted to this year's stock?
No, it was
Last year's stock or so, or Fox, yeah, some top conference at least, one of these, yeah. So there's a lot happening, and if there's a near linear runtime, who knows, right? In principle, I mean, there's hope that there might be some polylog result at least to come up with a good approximate solution for max flows. That's one of the topics that we have never really looked at too closely, I must admit. So
I believe at least for undirected graph polylog, a 1 plus epsilon approximation should
okay.
be possible pretty efficient.
Okay. I should mention that there are also some very primitive approaches that allow you to converge to a max flow solution. For example, the gradient descent approach. You might remember, for example, in like standard algorithms course, when you deal with max flows, you know Goldberg's algorithm or the push relabel algorithm. You know that? Where a flow is basically pushed downhill, where you have kind of a pre-flow, where you basically push more into the network that it can handle. And you try to resolve that you push more flow into the network that you can handle by basically adjusting the heights of the nodes. So that overall you find a waterfall solution that gets your flow perfectly from the source to the target. People have looked at this approach also in the distributed context. Yeah? And it turns out if you use this very simple gradient descent approach where you like really send flow downhill, where you consider messages as flow building up in nodes, and you send a flow, like you send a message from one neighbor to another whenever the pile of messages is in a way that the starting node has a higher pile than the next node at the next level. So in some sense, you emulate flow by just sending messages downhill. Yeah, if you look at buffer sizes, you can actually show that this approach will eventually converge at a max flow solution. Well, you can, let's say, carve out a max flow solution. But the problem is that this takes quite a long time to converge. Another approach is if you are able to generate random spanning trees. I don't know whether anything close to that has ever been tried. To obtain random paths between S and T, where the accumulation of these random paths might also tell you in some sense which direction to send flows along, but I don't know, I have no clue. Okay, so but if Fabian says that it's doable with all the techniques that are around, so polylog seems to be within reach. Another problem that is somewhat interesting is network monitoring and repair. So imagine that V, E forms a well-formed, so we already established the well-formed tree, and let L sub T be the set of local edges at time T. So you have a local network that changes all the time. Yeah? Where T might be set in an arbitrary way and might also change in an arbitrary way from time to time. So we don't even require connectivity or any predictability for the local edges. Yeah? And what we want to do is choose a global edge set ST at every step T, so that for every time window of size capital T, the set of all edges with the local and global edges together form a connected graph. Yeah? And where T is as small as possible. So, and of course also the global edges should be as small as possible ideally. I forgot to mention that, right? So you want to invest as little effort as possible to make sure that the local edges together with these helper edges form a connected graph, because then you can still make sure that broadcasting and so on works well. Yeah? Here, for example, there is some really nice random linear network coding result that where people have shown that if the graph is guaranteed to be connected at any point in time, then you can broadcast k messages with random linear network coding in O of n plus k time steps in a completely unpredictable network where the connections change all the time. It's like a really, really nice result about making use of network coding. Yeah? So a node basically doesn't have to know anything about what the receiving node node might know about. Yeah, so it gets some connection to some node, it just pushes out some message that is kind of a random linear combination of all the messages that it has received so far, and it just works out. At the end, after O of n plus k rounds, all the nodes can decode all the k messages and everybody's happy. Yeah? Amazingly, it works with coding tricks. And if you can at least guarantee connectivity, if you collect all edges with respect within a time interval plus t, it grows by that factor. Yeah? It's at least guaranteed then that within O of n times capital T plus k rounds, all the nodes have received messages. Yeah? So what you want to do is you maybe for some target capital T to make S sub t as small as possible. What would be a simple approach? Can you imagine what approach to go for after all that knowledge that I gave you?
Can you make S symmetric?
Oh yeah, but then you would have to invest the linear number of edges in each round, so that might not be so good. So of course, since you have a well-formed tree, or like you already assume that you have a well-formed tree, you could just offer all the edges of the well-formed tree in every round, which gives you like O of n edges. But maybe the graph is connected all the time, and so why should you invest so many global edges? Right? So you want to invest, let's say, only a little bit more than, let's say, a global algorithm would have to, like an offline algorithm would have to invest, that knows somehow what's going on. That can inspect the edges that it sees at each time step and can exactly add global edges wherever connectivity is not available. So basically, if your local network falls apart into k connected components, then k-1 edges is definitely sufficient, global edges. Yeah? But the problem is, our hybrid solution can't discover that so quickly.
So the nodes know when the edges disappear.
The nodes know which edges are available and which are not in each one. Yes, that we assume for the local edges. They do know that, and they can store that as well in their memory, right? They know, for example, oh, at round small t, I had this neighborhood. So they can remember that and recall that we still have this well-formed tree connecting all the nodes, so we can use the global edges in order to collect statistics about what's going on in the local network. Yeah? So in principle, we have a chance to figure out how many connected components we have in the local network at a particular time t. The only problem is we only know that fact after some delay, right? Because we have to do some aggregation via this well-formed tree to the root until the root knows how many disconnected components, connected components we have. What would be the simplest approach so that at least we come up with some polylog result? Yeah? The simplest approach would be we just run the well-formed tree algorithm for every round small t. Right? We just run it like in parallel with all the well-formed tree algorithms for other rounds. Yeah? We just run it, and what do we get? We identify that eventually each connected component for some round t will form a single well-formed tree, and then it terminates. It notices when it terminates, right? Because remember, I said before that the well-formed tree algorithm doesn't have to know it. It knows when it terminates because it terminates when the nodes of the well-formed tree don't discover any other nodes in the neighborhood anymore that are connected to a well-formed tree. Yeah? So at that moment it terminates. Yeah? So then a node can, and the max ID node also then knows that it's the root of the only well-formed tree that is left in its connected component. So it can basically set a flag. Like, okay, I am the root of the well-formed tree of my component. Right? And like it's just, let's say, a bit. Yeah? And then all we do is we just add up these flags towards the root in the converged cast in this global well-formed tree connecting all nodes. Yeah? We just collect these flags in the root, and then we know how many connected components we have. And then we know exactly how many global edges we should have added at time t. to have connectivity at time t. So we can be optimal with respect to a best possible algorithm that has global knowledge, but with a delay. Yeah, and the delay, if we just use the approach that I proposed here, is log n squared, which is bad. Yeah, it should be possible to do it faster. Of course, then we can throw in all these improvements to get it down to log n, but still the delay would be log n, right? And the question is, of course, whether it's the end of the story or not. So that's just an approach that I just presented here with the log n squared. The other thing is also somewhat interesting. There we add deadlines with it. So it performs a well-formed tree, and it can change in an arbitrary way over time. We have a source node S, and we want to send a message to everybody within a certain deadline t. Yeah, and we want to have a deadline because if it's not possible to come up, otherwise it's not possible to come up with an online algorithm. If we say we just want to make sure that eventually every node receives the message, then we don't know how long to wait. Yeah? An optimal offline algorithm that knows everything in the future, of course, knows whether in the future it will be possible to send a message to all other nodes. But an online algorithm, how can it know, right? So you need somehow a deadline to be competitive with an offline algorithm. Because otherwise, what can you do? Of course, there are two different approaches. You just keep adding extra global edges obliviously. You don't care about the structure of the network. You just keep adding them. And by the way, this approach might also be usable for the previous one, where we just worry about connectivity. Or we just add extra nodes edges adaptively based on knowledge that we have of the graph. Obliviously adding extra global edges gets us quite far, surprisingly, because there's a paper just from a bit more than a year ago about smooth analysis of information spreading in dynamic networks. It says, consider any dynamic network of size n guaranteeing connectivity in each round. With high probability, random broadcast solves the k-message broadcast. So random broadcast basically just means that in every node around, a node inspects its local neighborhood that it has at that round. Yeah? Remember that the local edges change unpredictable from round to round. So each node inspects its local neighborhood, picks one of these neighbors at random, and randomly decides which of its messages to broadcast there. Very simple random broadcast approach. It solves the k-message broadcast in O of k times n to the power of 2/3 times log n to the power of 1/3 divided by r to the power of 1/3 rounds if r random edges are added in each round. Yeah, so it so basically adding edges basically just a few edges, right, can already have quite some impact on can reduce the diameter of the network by quite a bit. Yeah? You don't need like n many random edges, but they somehow also noticed that there is that edges can have a significant effect on the worst case diameter. Which is kind of nice. It doesn't get all the way down to log n, because if you have n many edges that you add, then this n to the 2/3 should be completely eaten up, so that or let's say you just, because with so many edges you can basically create some kind of an expander graph connectivity, and then you should be done within log n rounds. Yeah, but this result doesn't give it, so it's definitely, the upper bound isn't tight. That's basically what I want to say here. The upper bound isn't tight. So adding random edges really has an effect on the diameter of the network and on the broadcasting time. And for hybrid networks, it's very easy, right? These random edges can just be added by making use of global edges that you just throw in. Yeah, or again, what you do is you check how well the messages are spreading over time. You keep monitoring that. And it's known that if the diameter is at least 2 ln and the expansion alpha of every, or let's say the diameter requirement is at least 2 times ln that you want to achieve, so that's your deadline, sorry. D is the deadline. And the expansion alpha of any subset is at least 2 ln divided by d, then the message from source S will reach all nodes within O of the deadline many steps. So if the expansion satisfies this property, then you are good enough, yeah, to reach this deadline goal. Right, and so in some sense you just have to keep track of how many nodes received the message, and then you just add global edges so that you achieve your goal. That's the basic idea. Yeah, I don't think that I should go through the proof because it's really just based on the expansion, how quickly your node set rises concerning the number of nodes that have been contacted, so that they also know the message. And here I assume that all the edges are used, yeah, that are available. Yeah, then it goes up with this 1 plus alpha to the power of t factor, with the nodes that already know the message. And just by doing some basic math, you see that within O of the rounds, if the expansion alpha is 2 times log n over d, you basically end up with informing at least like half of the nodes. And as I said, it's really just basic calculation. I don't think that we should go through it here right now. And I can definitely make the slides available now, so you can also have the look at the slides afterwards. It's nothing deep, nothing really too important. So here's a simple heuristic, yeah. And as I said, I haven't given it a deep thought. Considering the following heuristic, in each round all nodes use flooding along their local edges to spread the message, and via converge cast along the well-formed tree, the root gets informed with the delay of O of log n rounds about the number of nodes holding the message at the beginning of time t, so that it knows how well it went, concerning the spreading of the message. That's in some sense the idea. And if the number of nodes holding the message does not grow by a factor of 1 plus alpha, because that's what it should, with this alpha being equal to, what I said before, 2 times ln divided by d. If it doesn't grow by this right expansion value, then just add global edges. From nodes holding the message to nodes not holding the message, so that this is the case, so that the global edges make up for the amount of time, for the lack of nodes that haven't been informed. That's all. And so, because everything is happening with a logarithmic delay, you get this additional factor, right? It's not that you finish everything by the deadline d, but because of the log n delay, in the worst case, it might end up as an additional factor on top of d. Yeah, so that is definitely true, but should be provable. The question is only how do we add global edges from nodes holding the message to nodes not holding the message, so that the load is evenly distributed. Remember again the H-graph. That's where the H-graph can come in. We initially organize all the nodes in a random H-graph. Notice that this is an expander, so that's good enough for our spreading. And in round t, all the nodes that have already had the message before round t, they will leave the H graph, so we just care about those nodes that newly learned about them. And we make sure that there are always sufficiently many of them, because we added additional global edges, so that this node set is sufficiently large. So basically, the nodes that are left in this H graph is really just the nodes that have newly learned about it, and those nodes that haven't learned about it yet. That's the basic approach. So those nodes that got the message, they just leave the H graph, and if these cycles are chosen at random, then it's relatively easy to remove these nodes within the log amount of time steps. So that we get rid of them, so that we repair the H graph to the set of nodes that have newly received the message or that haven't received it yet. Because the nodes that are leaving are kind of randomly spread. And that makes sure that the nodes that are leaving do not form long consecutive sequences. And if they don't form long consecutive sequences, then the nodes that are still in the H-graph can easily be informed. Because the sequences can be at most logarithmic length, so again, making use of pointer doubling, we basically introduce the corresponding endpoints in log n time. And then we easily know how many new nodes there should be if, let's say, 1 plus alpha to the power of t minus 1 nodes have already been informed, because then it will be alpha times 1 plus alpha to the power of t minus 1, which are these new nodes. That should be the goal. But maybe we fall short of this goal, so maybe we need an additional k many nodes to reach this goal of this expansion. So then we just add the corresponding number of edges in that random H-graph. So among these blue edges, basically, we add a random collection. And what we simply do here is, so if the root notices that for some round 2t an additional k many nodes need to be contacted to reach a total number of alpha times 1 plus alpha to the power of t, it asks every one of the alpha times 1 plus alpha to the power of t minus 1 new nodes to inform on expectation k divided by alpha times 1 plus alpha to the power of t minus 1 of its neighbors in the H-graph, which would raise the number of new nodes for round t plus 1 to, and then I just need to sum up the formula so that it gets back to alpha times 1 plus alpha to the power of t. So it's not really deep, right? It's really just that we throw in enough of the edges in this random H-graph so that we can make up for non-informed nodes. Note that collecting information about how many nodes are contacted locally in round T and asking new nodes to contact additional nodes, of course, we can just easily collect that information in local rounds. Unfortunately, just some comments. Even though this algorithm might be working reasonably well in practice, it's not competitive against an optimal. Wait. Did I say that? No. I know the competitiveness because an optimal algorithm might just wait in one round, because even though the expansion in one round is really bad, in the next round the expansion will be good enough. That's why it's a heuristic. Now I remember. It's a time ago that I used these slides. Because there can be always one round where the expansion is really bad, but in the next round the expansion might be super good for the local edges. And then our heuristic throws in a lot of global edges in one round just to discover in the next round that would not have been necessary. Right? So our heuristic does much more work than it should have done. That's the basic problem. That's how it's really hard for it to be competitive against an optimal offline solution that knows the future. Because if it knows that in the future the expansion might be great, then it does not anymore. It just leaves it as it is and adds no global edges. That's a dilemma. So maybe there is no perfect solution, but this is really just a trivial one that even doesn't get us all the way to the end result. So in the worst case, of course, what an algorithm would have to do is it just collects the information over all D rounds to the deadline, and then based on that would have to decide what to do. Okay. Any questions up to this point? Yeah.
Well, the bigger question is perhaps, has somebody tried to connect these results to the initial practical applications you started to mention? Which assumptions are justified here in the practical setting that we're making here? Or not?
Yeah, not yet, although I would expect that hybrid networks are the right solution, for example, for vehicular networks. Because the problem is, especially at the beginning, that not all of the cars might be equipped with wireless devices. So it's not sufficient to establish connectivity along highways and so on. Yeah, so therefore you always have these interruptions somewhere, and therefore you have to fix this by adding global edges. So that you really get connectivity. Yeah? And also the global edges can be very useful in order to quickly collect information, much more quickly than would be possible just via the ad-hoc connections between cars. So to my mind, you know, really using both types of edges will give you much more effective vehicular networks than just relying on ad hoc connections.
So you're saying that's the area where you see it most likely that it's going to be applied?
Yeah. In general, I think for wireless networks, I think it could be extremely useful.
And moving topologies, or like changing topologies?
Yeah, for example, one way also one can use these global edges is, have you heard about Delaunay graphs? Delaunay graphs come from this area of computational geometry, or basically that's an area where people use them. It's a very easy rule, so imagine nodes being spread in this two-dimensional space, yeah, Euclidean space. And you connect two nodes whenever you can draw a cycle through this circle through these nodes that doesn't include any other node inside. Whenever there's no node inside this circle, then you have an edge in the Delaunay graph. And what turns out is that in non-pathological cases, so of course there can always be the situation in pathological cases that 4 nodes lie exactly on one circle, for example, or let's say 3 nodes lie exactly on one line. Let's avoid these. Let's assume that they don't happen. That there's no set of 3 nodes that perfectly aligns, or there's no set of 4 nodes that are perfectly lying on one circle. If this is true, then the Delaunay graph is always a planar graph. And even more so, it's a geometric spanner, in a sense that in the Delaunay graph there's a path from any node to any other node whose length, so if you sum up the Euclidean lengths of the edges that you're traversing in this path, is only by a constant factor larger than if you take the Euclidean distance between these nodes. Yeah, so it's a very nice abstraction of the Euclidean distance relationships between the nodes, because you can basically use the shortest path distance in Delaunay graphs to, you know, reflect the Euclidean distances between any pairs of nodes up to a constant factor. Yeah, and since it's planar, it means that on average, basically the total number of edges is just O of n, so it's really sparse, which also means it has a low aberricity. Which means that you can also nicely use these techniques that I presented here. Yeah, because you can share responsibility of the nodes among other nodes so that you can easily emulate also Delaunay graphs. In case you do happen to have a high degree somewhere. And Delaunay graphs are a really nice abstraction to speed up routing in wireless ad hoc networks. Because you know, you see, like, there are local routing algorithms that tell you which edges to take to get from any source to any target in a Delaunay graph. So there are online routing algorithms that can figure out which edges to take so that the path you are taking through a Delaunay graph to get to a target node, of course, given that you know the position of the target node, you need to know that, yeah, in the Delaunay graph. If you know the position, then there's an online routing algorithm that gets you really to this target node with just a constant factor, along a path that's really just a constant factor larger than the Euclidean distance between these nodes. So you can really find these paths also in an online fashion. It's not just the existence of these paths, yeah, that they exist. And so what you can do is you can emulate routing along the Delaunay graph as long as you can use local edges. And whenever you can't use a local edge anymore because there's too much of a distance between these nodes, And this usually happens if the nodes are not densely distributed in an area, but there are some sparse distributions somewhere because there's a lake, for example, yeah, which basically cuts through the path so that you can't use it via a local edge. At that point, you switch to the global edge. Yeah, because normally it means that there's an obstacle in the way, or whatever, right? Some area at least that is unpopular enough or hard enough to get there, so that people are just don't dare. Yeah, they're not there with their cellular devices or so. You just use a global edge to jump across that. And the problem with finding good routing paths in ad-hoc networks is gone. Yeah. It's great. So therefore, that could be a very nice solution to communicate in wireless ad-hoc networks, just by establishing a Duolingo graph. And it's known, I should also say that, it's known how to construct a Delaunay graph for any set of nodes, for any initial graph that they form, very quickly in a self-stabilizing manner. So in the sense that no matter what kind of initial graph topology you start with, by just doing local interactions between the nodes, they can converge towards a Delaunay graph just by local knowledge of the neighborhood and then knowing which edges to give up and which edges to keep, so that ultimately a Delaunay graph is found among the nodes. So there is an algorithm that basically works so that it can easily adapt itself as the nodes move. Yeah, so that you can easily maintain a Delaunay graph. And that's important because then, coupled with this online routing algorithm for Delaunay graphs, you can then get the best of both worlds in some sense. Yeah.
Okay, thank you. So you're saying yes, the area, but I am saying now, let me just answer from my experience in the consensus literature blockchain. We have done this for 40 years or 30 years. Nobody was interested in practice, but of course we did a lot of research on this. And when it finally comes, it's not exactly the same problem that people are trying to solve in practice, but then one has to make sure that they are not rediscovering the things we had discovered a long time ago. Because the theoretical research has moved on usually, right? The theoretical research has gone on to some other place. But that's, yeah, I mean, it's good to know that, yeah, these models have to fit. And let's see how they actually will fit.
Yeah. Actually, I wanted to show slides about the Delaunay graph. I just noticed that, unfortunately, I don't have them here with me, which is a pity, because otherwise I could have shown to you also how that works. Any further questions? There are also some security implications that I can mention here. Because the global network has one big problem. Yeah, because I mentioned that every node can just introduce the address of its neighbor that it knows to other neighbors, so that other neighbors now can connect to that neighbor. Right? That's what I mentioned for the global network. You have full flexibility for the changes of the address. Okay? Do you see any problem with that? There's a fundamental problem with that. That's also a problem that is that the internet is suffering from. Because how do denial of service attacks work in the internet? You think about it. There's a botnet. They are sending messages all to a single address, right? And why can you do it so easily? Because you can easily share an address with tons of nodes, right? So in some sense, the way you connect to the internet, if you think about access control, it severely violates access rights. Yeah? That's a problem with global networks. It's not a problem with local networks that, where connections are given by, let's say, cable networks or it's a different domain, yeah, where you are not dealing with this problem, yeah? Or like in wireless ad-hoc networks where the local edges are really like connections that you can establish whenever you are getting within range. you can't do these things that you can like come up with massive attacks. Although, I mean, even in wireless networks, of course, since you have a shared medium, you can jam the channel, and make it unavailable to any nodes within your vicinity. Of course, you can play these tricks, but they will only have a local effect, And in the internet, there's basically no limitation, right? You can reach anyone else in some sense in the internet, and that's a huge problem. So, since we have still some time, shall I talk about this, or do you want to know any other aspects of hybrid networks? Yes?
I have a highly related question.
Okay.
I know that you mentioned that we're not talking about Byzantinos today, but I was wondering what else research you could say with Byzantinos, since these Byzantinos can be better more nodes and so on.
Yes. So, there are basically two possible approaches to protect. So of course in a local network you have a hard time because the local network is not under your control, and if the degree is relatively small and the adversary can pick any nodes it likes, you are easily dead. So usually if you want to do consensus in a local network, just with a very few adversarial guys you can isolate nodes potentially, even a large fraction of the nodes, if there's a bottleneck somewhere in the network, and it's game over. So the local network, with the global network, of course, since you can, for example, rapidly change connections, you can make it much harder for the adversary, right, to attack the network. So then usually, if you think about these overlay networks, these global networks, there are two possible strategies. One is proactive, the other one is reactive. So the reactive strategies, they just try to fix the network after the fact. So basically a huge adversarial attack has happened on the network, and now it releases its attack. And the network might be in a completely dysfunctional state, but it's still connected. Let's assume it's still connected, But it's like completely, like the nodes are completely weirdly connected because the adversary completely confused the nodes. So
is this related to strict stabilization?
Yeah. So then what you want to have is that you want to have overlay maintenance protocols that are self-stabilizing in the sense that you can get from any initial topology back to your desired topology. There has been quite some research on that. So there are various self-stabilizing protocols for various overlay network topologies that you worry about. So it's kind of amazing how far you can go there. So that's a nice direction. That's one way of protecting yourself. Then there are so-called proactive strategies. The proactive strategies are those strategies where you try to organize the nodes into random quorums, or basically into local groups that always have to do something based on majority decision. And you want to collect nodes randomly so that if the adversary only owns a random fraction of the nodes, hopefully then also it's like a sufficiently low random fraction, hopefully then in each group of O of log n nodes, it will still be in the minority with high probability, so that you can use standard consensus protocols to wash out adversarial behavior. But the problem is that these proactive approaches are extremely expensive. Because it sounds nice at first glance if you hear O of log n, but remember that log n, even like for reasonably sized networks, is easily beyond 10. And the O in is also at least 10. So you basically have to have these groups of size 100 easily. And remember that if you run a consensus protocol, then you easily end up with because like everybody has to contact everybody else, and you have 100 squared. Communication that you have to do. And that's just to emulate one reliable node. You have like 100 to the square many messages, which is ridiculous. It's completely ridiculous, completely outrageous. Which shows that using proactive approaches that protect an overlay network, as long as the adversary knows it's only a constant fraction, is not working well in practice. So in fact, also there we have been thinking about hybrid approaches. Because what if you have a so-called supervisor? Yeah? So imagine there's one reliable node. Yeah, maybe that node that initiated the system, right? There's some user and whatever he set up some server or some gateway that people can connect to so that they get into this overlay network, right? So you can trust this gateway, yeah. And so that gateway can then always serve as a last resort. So if everything breaks down, then the nodes contact the gateway again, right? And the question is, if you do that, can you at least design protocols where in normal operation the gateway is only rarely contacted by nodes? Of course, if it really goes wrong and the adversary starts a heavy attack, then the gateway might easily get overloaded. Yeah? But under normal operations, then the gateway can serve at least as a safe anchor so that you can hopefully also repair the network much more quickly. Yeah. So that is definitely something one can think about. Yeah? Or in the advent of clouds, you can also combine peer-to-peer systems with clouds. Yeah? In some sense, the clouds would then also serve as a safe anchor. And the nice thing, at least, about the cloud is that it won't be possible by the adversary to attack the cloud, because the cloud normally has such a huge amount of bandwidth that it would be surprising if, let's say, an adversary would manage to shut down, let's say, the Amazon cloud, yeah, or the Microsoft cloud. That's probably tough. Yeah? So at least you know that there is no single bottleneck anymore. The cloud will handle it. And what you then do is you charge the peers for the requests that they send to the cloud, right? So they should only do it as a last resort, but whenever they do so, they have to pay something, because the cloud is not for free, of course, right? So if an adversary wants to start a massive attack, it's really going to be expensive for the adversary. And so immediately have incentives not to start any denial of service attack, because otherwise it will get really expensive for the adversary. Yeah? That's, I think, an interesting way out. Yeah? Where you can combine the advantages of both worlds. And that's probably what I would go for in practice. To get the cloud involved, but not that the cloud is essential, not that you have a lock-in situation. Yeah? So in a sense that the peer-to-peer system, if it's unhappy with one cloud, it just migrates to another cloud. Yeah? Because it's always bad if you have a lock-in situation, because the cloud has knowledge that is essential for the operation of the peer-to-peer system, which would potentially create problems. Yeah? So in general, therefore, also they are hybrid solutions, I think, are the right way to go for in practice, where hybrid comes in here now that you have these two classes of nodes. Yeah? They're very powerful nodes, but costly. You have to pay, right? And cheap nodes, but potentially unreliable. So also there, one can think about potential solutions. Any further questions?
Is there a class for this? Is anybody use enclaves or something?
Which one?
Enclaves?
Enclaves. Oh, what is that?
Internal thing is that you trust is computation and that your adversary cannot corrupt.
I think most know.
Trusted computation. Yeah.
Enclaves.
The problem is Intel tried that, right? With this.
Don't use the word try.
But it was a nice try, because at the end there were so many attacks that came up with this trusted environment.
It comes back with your knowledge.
It comes back.
Yes.
Ah.
I mean, Intel was not the only one. I think it's something that is becoming quite universal to add some features for having security in the hardware itself.
Yeah.
As a complementary measure, of course, you cannot escape crypto in the end.
Every device like this has one. Yeah?
Yes.
It's just not as powerful as the SGX mode.
You have just
CPU, right?
You have just zone here. ARM is one who really led the movement, and then ARM has a new specification specification, CCA, it's going to come in ARM version 7, I think. 9, but it's ready, it's completely standardized, except the chips are not here yet. And AMD has some solutions, and Intel has the new generation coming.
I mean, to answer your original question, this is not an alternative, but rather, as Pascal also says, complementary. Right? We have many layers in a practical system. And one layer will be the trusted hardware for your piece, or maybe for more, for doing some computation. Whether it can reduce the communication, maybe not. Yeah? You still have to communicate. Yeah.
And the nice thing is, trusted hardware could also significantly increase the robustness of overlay networks. By the way, if you have trusted hardware in between your computer and the outside world.
I mean, my question would have been now, of course, since we're talking about malicious attacks, and you said everybody is nice and so.
Because
about malicious, how little do I have to do to break these algorithms?
Because are you aware of this concept of reverse firewalls? Because normally firewalls only filter at the end, right? At the target. Because the messages come from the outside world to the target, and there's a firewall before that, and it checks whether this message is legitimate or not. If it's legitimate, it lets it through. If it's not legitimate, it throws it away. But the problem is that at the target, it's often too late, right? So what you do is, you want to have the firewall at the sources, yeah, or close to the sources, as close as possible. So basically, already when the source injects a message, at that point, you have which is called the reverse firewall, which just checks whether the message should be let into the network. And if this firewall discovers, oh, it shouldn't even be let into the network because it's definitely illegitimate, and you filter it out there. You filter it out at the source. There, it's not too late. That's the right place where to filter out messages, yeah? And when you look at the way ISPs do it, that's exactly what they try, yeah? If they discover a massive denial of service attack, they try to shut it down as close to the sources as possible, yeah? So that it doesn't get even into the network. Yeah? And that's the hard part. That's the real hard part. There's a lot of, at least what I heard about is that there's a lot of manual intervention that is needed. The automatic tools, they are not so good because how can you distinguish legitimate from illegitimate traffic? That's a major problem. People throw machine learning at this thing to figure out what could potentially be illegitimate traffic by their pattern. Yeah, but it's really hard. At the end, the human needs to decide. Yeah, and human has to come in because maybe the machine learning algorithms cannot work reliably enough. And that's, as far as I remember, that's a big thing among the internet service providers to come up with effective filtering tools. And that basically addresses this problem that I wanted to raise also with this access control, because it goes into the right into the direction. If you really want to be effective concerning access control, you have to enforce access rights at the source and not at the target where it's too late. And that's where trusted hardware can come in. Yeah, where trusted hardware can be inside of a computer, so that even if the adversary takes over your computer, the adversary cannot use your computer for denial of service attacks. It's doable. Yeah, the concepts are, to my mind, there. If you are interested, I can present you the solution to make global communication much more reliable. So, maybe you have some other questions as well.
In your example, let's say we do have trusted hardware and reverse firewall at the source. How can you prevent a distributed effect, or if you have many sources that send one packet roughly at the same time, it will, from the source viewpoint, be perfectly legit. It's only one single packet. Whereas it's the only packet that the source is sent. But then when they will collide, of course, at the destination, then things will create evil. So it seems that we really need both, right? It's not like...
Sounds a bit strange, right? Because if you have full freedom in order to change your connections in the overlay network, I mean, it's legitimate to use any connection that you have. Why should you filter out packets, right? For a connection that you have in your overlay network. Doesn't make too much sense, right?
It does not indeed.
Exactly. Yes. So that's why you need a slightly different concept of managing overlay networks. And that can solve this problem. even though it sounds surprising, but what you need is an effective access control mechanism by the targets of messages. The question is, how can it be done?
So are you saying that targets will push back information to the source so that they can figure it out?
Yeah, but before that, they have to know which connections are legitimate connections and which aren't.
Yes. So how do you solve that problem?
If you want me, I can talk about it.
Well, I think why not? I mean, if you can solve it, I'm just curious because it's indeed it's a big problem.
Yeah.
So,
So let's say I'll just give you a very quick summary. So, so there are certain admissible primitives that people have been using in this self-sterilizing overlay network field that you can use in order to make sure that connectivity is always preserved, but you still maintain universality in the sense that you can get from any weakly connected overlay network topology to any other weakly connected overlay network topology. And for that you just need 4 primitives. One is the introduction primitive, which I already talked about. So a node that knows V and W can introduce V and W to each other by sending the address of W over its connection to V. Right? That's a way how you can establish a new edge in your overlay network. Special cases, of course, self-introduction. A node can also introduce itself so that a backwards edge is established. Don't worry about these dotted edges. They are just meaning that there are messages on the way with that address, and once it's received, it's like a solid edge, because it then can be used by a node. So there's the introduction primitive. Then the delegation primitive is where a node just wants to give up a connection to a node. It instead delegates it to one of its neighbors. That's the delegation primitive, and obviously it also maintains connectivity. There's nothing wrong that can happen here. It can happen here. Then there's a fusion primitive. So if a node U has redundant connections to another node, of course it can throw one of these connections away. No reason to keep redundant the address of V in a redundant manner. Sufficient to keep it once. Then there's a reversal primitive where a node just, in some sense, reverses the direction of an edge, because the direction of an edge always says who knows about whom. And instead of U knowing about V, if U sends its own address to V and then deletes its link, then it somehow it looks like the edge is turned around, because now V knows about you. And it turns out that these 4 primitives are sufficient for universality. They are not just, so first of all, they can be executed in arbitrary asynchronous environments. They're locally executable, wait-free, in a wait-free manner. You don't have to wait for any other node to respond. It's just fire and forget to execute these primitives, as I said, in arbitrary asynchronous environments, truly arbitrary, as long as the underlying communication network is reliable in the sense that it promises that eventually the message will surface on the other side. So these primitives are really widely usable, and introduction, delegation, fusion preserve even strong connectivity, and together with reversal also weak connectivity is maintained. And they are universal in the sense that you can get from any topology to any other topology. So that's a nice message, but they violate access rights, and that's where we run into a problem. Because whenever a node introduces W to V, maybe W doesn't want U to introduce itself to V. And the problem is that W has no control on who is allowed to connect to it, which is a severe issue. Because that's the origin of any kind of denial of service attack. You can easily share information about accessing a node, connecting to a node. And then the node is doomed, the target node is doomed. So W cannot control who has access to it. So there's no clue how many nodes are currently knowing W. And U also cannot revoke its decision, because once it has passed on the right to V to connect to W, that's it. You cannot tell V, oh please, remove the address that I sent to you to W. It's too late. the information has been shared. So why do we care? Well, because of US attacks. Yeah? Okay. So the problem is really with introduction and delegation. These are the dangerous operations, the other ones are fine. Fusion and reversal there. A node is always in the loop, whether it's whether it wants to have this incoming connection or not. The solution to that is to make it more to keep nodes in the loop. For the connections is to use a concept called relays, where you make it more explicit, the connection. So you have, you can also consider these as ports. Yeah, every node, when it has a connection like from U to V, it's like it has an outgoing port and V has an incoming port for the messages, right? And now here's a safe form of introduction. So the node U can still allow V to communicate to W, but it can only do it via itself. So the only thing that U manages to do is establishing a connection from V via U to W. So it can basically share information about its relay connection to W, which will then allow V to send messages to W via U. And that's why I call it a relay approach. Yeah? So U doesn't have the right to give V direct access rights to W in the sense that if I would now consider just the standard firewall of W, the standard firewall of W would filter it out. Yeah? So that's a much safer form of introduction. You just have indirect connections via the node that did the introduction. Yeah? And then, in some sense, no access rights are violated because anything that V sends to W, you could have sent as well, right? I mean, information theoretically at least, there is no difference. And V cannot send more messages than U has bandwidth to W. So in some sense, denial of service attacks cannot be started anymore because if someone wants to share its connection, its access right with many others, then it still has to go via that poor single node. Yeah, so that's in some sense the idea. And revocation is also now easily possible because if U doesn't want V to send a message to W anymore, it just kills its relay. It's as simple as that. Yeah? Of course, U also loses its connection, but also V. Right? So of course you have to make sure that you use then certain relays only for indirect connections so that you don't kill your own connection whenever you want to revoke access rights from other nodes. This then serves this principle of least exposure, which is actually quite important for distributed systems. Of course, then you can establish some kind of trees, right? Because someone can introduce the others via itself to node, and they can also do some established connections. So you basically can create these arbitrary trees, relay trees. Yeah. And it also looks like you lose universality, but you don't. So there is a proof that's showing, I skipped these things. But there's basically a proof, no, I skipped that. So basically, this relay concept still allows you to get from any or weakly connected overlay network to any other. Weakly connected overlay network. I skipped that one. I just want to get to this reverse firewall concept. Because what you really would need is something like this here, right? You need a trusted communication layer inside of a computer that basically manages the relays. That's what you would need. So in some sense, the computer just has a local ID of a relay. So it knows which relay to contact in order to send information via the internet to another node. Yeah? And now you can perform source-based filtering because if the other node decides to shut down this connection, you send it basically because this trusted communication layer is the first that receives the message. The computer, whatever's running here can't filter out that message because it will definitely reach this trusted communication layer. The trusted communication layer, if the target tells it to shut down a relay, it shuts it down. But then it acts like a reverse firewall because now if the computer still tries to send messages via that relay connection, the trusted communication layer won't allow it anymore. But for that you would have to have this trusted communication layer, which which unfortunately I think is not around yet. Yeah. But I think it would be very useful for this global network, because that is a very important issue that they are still plagued with, that this total freedom of sharing addresses, yeah, and this total freedom of changing networks this way is too much freedom. Yeah? You want to have a more tighter, you want to have a tighter grip on these things. It would be nice to have that. Should also be easy to build these things. So if really a group of people wants to come up with a much more secure overlay network, they could just buy simple boxes, I guess, and just set it all up so that even if one of them is taken over by an adversary, couldn't use that as for insider attacks concerning, like, at least from the perspective of starting denial of service attacks, which is normally the hardest thing that you have to deal with for overlay networks, because it's the hardest to avoid. Yeah.
I think it might be true what you say, only if you don't want your service to be accessible by anyone on Earth, in which case it would be very hard to do.
Yeah.
There are people who have dedicated their careers to building security.
Yeah.
It's not easy at all.
Yes, exactly.
They can tell you about it if you want.
Yeah.
Because that's the fundamental that we will assume, right? That the service is accessible by anyone, right? That Netflix should be accessible by anyone, and Netflix wants to be accessible by the web as well, right? So making a network in which you have like safeguards, and you need to find a relay. When you are increasing the barrier to access the service in the first place, which then there's the question whether it's really. What is the cost versus the game? I guess you still have DDoS attack on the internet, it's easier to use, versus you need to actually work yourself into communicating much more. And then there's DDoS attack. You have more state in the system as well, right? I mean, you trust hardware.
Yes.
So it's also not clear, right?
Yes.
Whether it's how much it is worth, and it's one we did also an economical analysis.
Yeah. I mean, the nice message is at least that normally for these very scalable overlay networks that we have considered in the past, the degree is fairly small. So you don't need many connections. Normally it's like in this order of logarithm, the number of connections. So that can easily be handled by a very simple hardware. And also if you think about how many connections your computer really keeps, like in normal mode to other computers in the internet, it's probably not so many, right? I mean, how many distributed systems are you running?
The computer, no, the relays will keep up with more. The relays will keep up with more connections. And those can handle billions.
Yeah, in some sense they would have to take over these TCP/IP connections. Yeah?
Yes,
for every TCP/IP connection you would need a relay, yeah. If you want to also integrate that way all the way into this TCP/IP. Yeah, that's true. So my idea would be that you use it like selectively, right? So for some high secure applications, you make use of this hardware, and for the others you don't. Which you can also do with your computer, right? You can use your platform module to store keys that are important for you, and for others you don't. Yeah. So you just selectively make use of this opportunity, but just to have that would already be, I think, a major benefit to my mind. Yeah? Because then other people in the distributed system can also enforce you to use it, because otherwise you won't be able to connect to anyone. Because the messages simply will not be processed by the other nodes. I mean, you could still try denial of service attacks if you figure out these nodes by other means. Normally you should just have a gateway to get into the network, and from that point on it should be hidden who else is connected. But if you, via some other crawling approach, can nevertheless figure out, of course, you can bypass all these security measures by starting a standard denial of service attack, but at least there is a possibility, at least if you stay within that concept, to then make overlay networks much more secure. So that it's worth investigating in that and building this thing at some point. I think it's really worth it, the effort. So I'm trying to sell it. Any further questions?
I guess not.
Okay.
Yeah, it's
Then
time
I
to-
think enough information for today, so thanks very much.